In the quiet of a clear night, as we gaze up at countless stars, it is easy to imagine that we see the cosmos as it truly is. But appearances can deceive. Beyond the glittering constellations and luminous galaxies lies a vast realm of unseen wonders. Much of our universe is hidden in shadows, mysteries woven into the very fabric of space, waiting for those curious enough to listen. Tonight, we embark on a gentle journey through these cosmic enigmas, exploring phenomena that confound our understanding. Our voyage drifts from the darkness that holds galaxies together to the force that drives them apart, from immense voids of nothingness to invisible gravity that tugs at us across the light years. Let us begin, unhurried and inquisitive, at the threshold of the unknown. High above in the cosmic ocean, galaxies spin like graceful whirlpools of starlight. If we gaze at a majestic spiral galaxy, we expect to see its outer stars orbiting more slowly than those near the glowing center, much as distant planets circle a sun more leisurely. Yet there is something odd about their dance. Stars at a galaxy's edge should drift more slowly than those near the core, but they do not. They whirl just as fast, as if gripped by an unseen force. It is as though an invisible halo surrounds each galaxy, holding its stars in a tight embrace and preventing them from flinging away into the void. Astronomers call this hidden mass dark matter, matter that neither shines nor reflects any light. We cannot see it directly, but we know it is there by the subtle gravity it exerts, binding galaxies together in its ghostly grasp. Astronomers first glimpsed this mystery in the 1930s. A distant cluster of galaxies appeared to have too little visible matter to hold itself together, yet it remained bound, as if some unseen mass provided extra gravity like cosmic glue. Decades later, in the 1970s, the evidence grew impossible to ignore. Vera Rubin, studying spiral galaxies, found that stars on the outskirts were moving far faster than expected. They should have drifted off into space, but an enormous hidden mass was keeping them in orbit. These discoveries made it clear that dark matter is everywhere, surrounding galaxies and clusters. Today, we know that about 85% of all matter in the universe is this invisible kind, outweighing the normal matter we see by a vast margin. Dark matter's true nature is a subject of intense speculation. Some scientists suspect it could be a new species of subatomic particle, one that fills the universe but barely interacts with ordinary atoms. Others wonder if dark matter might be a multitude of tiny, unseen black holes born in the newborn universe, or something even more exotic. A few have even proposed tweaking the laws of gravity to explain away the need for dark matter. But those modified theories have struggled to match all the observations. For now, the particle hypothesis remains the leading idea. If dark matter is made of particles, they must be extraordinarily shy. They slip through Earth and through our bodies without a trace, interacting only via gravity. What kind of particle could behave like a ghost, yet collectively weigh so much? That question continues to confound physicists and astronomers alike. Even now, as we move through our daily lives, dark matter is all around and within us. Scientists estimate that each second, countless dark matter particles stream through your body without ever colliding with a single atom. Ghosts passing silently through empty space. We remain oblivious, yet their gravitational influence is woven into the universe above, holding galaxies in its sway. Decades of experiments have tried to catch a whisper of these phantom particles, deep underground or far in space, But so far, dark matter has evaded every trap. Its true identity, whether an exotic particle or something stranger still, continues to elude us. It is a silent reminder of how much remains hidden in plain sight. In the meantime, physicists have set up extremely sensitive experiments to try to catch a dark matter particle in the act. Deep underground, where the bombardment of cosmic rays is muted by layers of rock, giant detectors lie in wait. Some are vats filled with ultra-cold liquid xenon. Others use crystal arrays or chilled semiconductor chips, all watched meticulously for the faintest possible signal. The hope is that once in a great while, a dark matter particle streaming through space might strike an atomic nucleus inside one of these detectors, producing a tiny flash of light or a subtle vibration. Years have gone by in hushed anticipation, yet no definitive whisper of dark matter has been heard so far. The detectors register mostly silence, broken only by occasional known particles and random background flickers. Still, the search continues, like casting wide nets into a dark sea and patiently waiting for a catch. This continued quiet only deepens the intrigue and the resolve to keep listening for the slightest murmur from this invisible ocean of matter. We do know that dark matter played a crucial role in shaping the cosmos. In the young universe, long before galaxies took shape, dark matter was already pooling into clumps under its own gravity. Ordinary matter, the gas that would later form stars, was initially too hot and energetic to clump easily. But the dark matter provided a gravitational scaffold. It formed invisible clouds and filaments, and its gravity drew ordinary gas into those patterns once things cooled enough. Galaxies ignited within these dark matter cocoons. Without dark matter's head start in gathering, the universe might have remained a diffuse fog for much longer, with far fewer galaxies formed by today. In a real sense, dark matter was the hidden hand that helped build the first galaxies and galaxy clusters. If we could somehow see dark matter directly, the appearance of the night sky would transform. Every galaxy you spot would be enveloped in a much larger, faint halo of dark matter, extending well beyond the visible stars. The Milky Way's own dark halo would reach many times past the edge of its disk, even overlapping with that of the Andromeda galaxy. You would behold not just isolated islands of stars, but vast spheres of transparent matter surrounding them. With such dark sight, we would also recognize that galaxies are not randomly scattered. They trace a vast pattern. Long, wispy filaments of dark matter, sprinkled with galaxies like morning dew, link clusters to clusters. And between these luminous strands lie enormous voids, nearly empty of both stars and dark matter. This is the cosmic web, a grand design shaped largely by dark matter's gravity. Without special instruments, we infer this structure from subtle cues, mapping the unseen architecture that holds the bright cosmos together. It is humbling to realize that if dark matter were to vanish, our familiar universe would begin to unravel. Galaxies like our Milky Way might not hold on to their outer stars. Those stars would slip away into space without the extra gravity to anchor them. Clusters of galaxies would fly apart, their member galaxies no longer bound into families. Even the vast tapestry of the cosmic web would start to dissolve without dark matter's scaffolding. Thankfully, dark matter has been with us since the beginning, silently keeping cosmic structure intact. We live in a universe where an invisible form of matter dominates by mass, yet we sense it only indirectly. This paradox, being surrounded by something so fundamental and yet imperceptible, is part of the poetry of the cosmos. It challenges and inspires us to find ingenious ways to uncover secrets hidden in plain darkness. The picture we have of the universe has forever changed. What we see, the gleaming stars and galaxies, is only a small fraction of what truly exists. The rest is this invisible matter, silently sculpting and governing the cosmos. It means that every galaxy rides along with a hidden ballast. Every cluster is swaddled in an unseen cloud. The universe is not just islands of light in empty space. It is a vast scaffold of dark matter, with the luminous matter merely sprinkled on top. Realizing this fills one with wonder and a deep humility that so much of the cosmos lies beyond our direct perception. Dark matter may act as the invisible glue holding the cosmos together, but it is only one side of the cosmic story. There is another mystery that seems, in some ways, the opposite. If dark matter pulls, this other phenomenon pushes. While unseen mass quietly binds galaxies, an unseen energy is making the universe expand faster and faster, as if space itself were stretching under a hidden force. Galaxies are drifting apart at an accelerating pace, carried by this mysterious influence. Scientists call it dark energy, a name for something we scarcely understand, a force that is driving a runaway expansion of the universe. For most of the 20th century, scientists assumed that the expansion of the universe, set in motion by the Big Bang, should gradually slow down over time. They reasoned that gravity, the same force that holds planets in orbit, would tug on galaxies and break the expansion. Many even thought that, given enough matter, the cosmos might one day stop expanding and collapse back on itself. But at the end of the 1990s, a startling discovery upended these assumptions. Astronomers observing distant exploding stars, brilliant supernovae in faraway galaxies, found that those galaxies were farther away and receding faster than expected. The universe was not slowing down at all. It was accelerating, as if some unknown energy were pushing everything apart. Interestingly, the idea of a repulsive force in space wasn't entirely new. Over 80 years earlier, Albert Einstein had introduced a term in his equations called the cosmological constant, essentially a repulsive force woven into space to counteract gravity and keep the universe static, as that was what he, and others then, believed the universe to be. Later, when astronomers discovered the universe was expanding, Einstein discarded this idea, supposedly calling it his biggest blunder. Yet, in an ironic twist, the concept has re-emerged. Dark energy is essentially a modern form of Einstein's cosmological constant, an energy of empty space that causes expansion to accelerate. Einstein's old idea was not so much a blunder as a prescient hint at what the cosmos truly holds. This baffling phenomenon was given a name: dark energy. The word dark here, as with dark matter, simply means our knowledge is in the dark. We do not yet know what this energy really is. It might be a built-in property of space itself, a kind of pressure from the vacuum that grows as space expands. Or it could be something entirely new, an unknown field or force saturating the cosmos. What we do know is that dark energy does not clump together like matter. It seems to be smooth, filling space uniformly and pushing outward on the fabric of the universe. Over billions of years, it has tipped the balance, overpowering gravity on the largest scales and driving galaxies apart ever more swiftly. In the early eons of the cosmos, gravity had the upper hand. For billions of years after the Big Bang, the pull of matter slowed the expansion bit by bit. But as space grew larger and matter thinned out, this mysterious dark energy gradually took control. To imagine how dark energy works, picture the fabric of space as an elastic sheet. Gravity tries to pull the sheet together in places, but dark energy stretches it from within. As the universe grows, there is more space, and thus more of this energy, fueling even faster expansion, a slow-motion runaway effect. The galaxies are like dust motes on the stretching fabric, steadily moving apart. Empty space itself carries this subtle energy, reminding us that a vacuum is not truly nothing at all. It has its own latent power. Scientists are striving to measure dark energy's properties with ever greater precision. They observe distant supernovae and map the clustering of galaxies across cosmic time, looking for clues. So far, the simplest assumption seems to fit, that dark energy is constant, the same everywhere and everywhen, an unchanging background force. But we cannot be certain. If dark energy were to evolve or change over billions of years, it would reveal new physics at work. Several new observatories, on Earth and in space, are dedicated to this mystery. They are surveying billions of galaxies and the cosmic web itself, hoping to see if the universe's acceleration has subtle wrinkles, or if it truly behaves like Einstein's cosmological constant to the finest detail. Today, scientists estimate that dark energy makes up nearly 70% of everything in the universe. Dark matter accounts for most of the rest, and only a sliver is the normal matter we touch and see. In a sense, the universe is dominated by this unseen energy. Its effect is subtle, yet inexorable. It steadily pushes galaxies away from each other. The implications of dark energy are profound. In the far future, it promises an ever more isolated cosmos. Trillions of years from now, distant galaxies will have slipped so far away that their light no longer reaches any other. An astronomer in that far epoch, in whatever galaxy they inhabit, might see only their own stars, and perhaps a few neighbouring galaxies bound to them. Beyond that, an endless dark void. All evidence of the wider universe would be gone beyond the cosmic horizon. This distant loneliness is the legacy of dark energy's push. It makes us grateful to live in an era when the sky is still rich with galaxies to observe, and it challenges us to learn as much as we can about this mysterious energy before time carries the clues away. What exactly dark energy is remains one of the greatest unsolved questions in science. Yet its influence is unmistakable. It widens the gaps between galaxies and forms ever larger stretches of nothingness. In fact, the universe is far from uniformly filled with stars and galaxies. Instead, galaxies collect in clusters and along filamentary strands, a vast cosmic web with huge hollows in between. Those hollows are the great cosmic voids, immense regions of space almost entirely devoid of galaxies, cosmic deserts, where only a few lonesome stars or galaxies wander in the darkness. In one famously empty patch of the universe, in the direction of the constellation Boötes, astronomers found a void so vast it was nicknamed the Great Nothing. Stretching roughly 300 million light-years across, this region contains almost no galaxies at all. By all expectations, thousands of galaxies should have populated that volume of space, yet only a few dozen have been observed. It is as if an enormous section of the cosmos were nearly hollow, a black expanse where creation placed almost nothing. The discovery of this Boötes void in the 1980s was a profound surprise, revealing just how immense and lonely a cosmic void can be. Great cosmic voids like this are not unique. Maps of the universe show a foamy pattern. dense clusters and filaments of galaxies separated by huge voids. These voids span tens or even hundreds of millions of light years, making up the majority of the universe's volume. Scientists believe they formed as matter gravitated into the surrounding walls of the cosmic web, emptying out the interiors. Over time, smaller voids likely merged into larger ones, creating these gigantic caverns of space. Though not completely empty, there may be thin gas or the occasional dim galaxy wandering through. They are the closest thing to true nothingness we have found on such an enormous scale. To grasp the emptiness of a void, imagine drifting through one on a journey between galaxies. As you left the crowded regions behind, the pinpricks of distant galaxies would grow sparser and fainter. Soon, you might find yourself in a vast gulf of darkness with hardly any lights in sight. The usual tapestry of thousands of galaxies that fills the night in rich regions would fade to just a few faint glimmers, perhaps a distant cluster far at the horizon of the universe. In every direction, there would be mostly black sky. The silence would be absolute. You could travel for millions upon millions of light years and not encounter another galaxy. Floating in such a void would be like being adrift in a limitless, starless ocean. One tantalizing hint of a supervoid affecting the universe comes from an unlikely source: the afterglow of the Big Bang. In the cosmic microwave background radiation, there is a curious cold spot, an area slightly cooler than expected, puzzling cosmologists. Some have proposed that an enormous void, perhaps 1 billion light years across, in that direction might be responsible. As light from the Big Bang travels through such an underdense region, it would lose a bit of energy, arriving a touch cooler. The idea remains debated, but astronomers have found hints of a large underdense patch of galaxies in that vicinity. If true, it means a vast void is imprinting its presence on the very light left over from creation. A subtle fingerprint of nothingness on the universe's oldest light. Our own cosmic neighborhood is not as extreme, but even here there are hints of underdense realms. Astronomers have identified what they call the local void, a relatively empty region adjacent to the group of galaxies that includes the Milky Way. It seems our galaxy might lie near the boundary between a dense filament, home to the Virgo cluster and other groups, and this local void of fewer galaxies. This could mean that on one side of the sky, galaxies are relatively plentiful, while on the other side, there is a vast swath of emptiness extending far beyond. Such a perspective reminds us that even our home in the universe skirts the edges of great emptiness. Contemplating such vast emptiness can be both humbling and oddly peaceful. It underscores that most of the cosmos is, in fact, empty space, and that the galaxies, with all their stars and planets, are like tiny islands of light scattered in a boundless sea of dark. We find ourselves living on one of those islands, on the fringe of a great void, surrounded by luminous neighbours on one side and silent nothingness on the other. In the face of that, the night sky's darkness takes on a profound new meaning. It is the backdrop of infinity, a gentle reminder of the sheer scale of everything beyond our little world. Not all mysteries lurk in emptiness. In fact, our own galaxy is caught in the grip of a massive but mostly hidden gravitational anomaly. Decades ago, scientists discovered that the Milky Way, along with our neighbouring galaxies, is hurtling toward a particular patch of sky at incredible speed. This motion is far above and beyond the general expansion of the universe. Our entire local group of galaxies is being pulled at over 1 million miles per hour towards something we cannot fully see. This unseen concentration of mass has been given an evocative name: the Great Attractor, a title befitting its mysterious pull on hundreds of thousands of stars and galaxies. Why didn't we see such a colossal thing immediately? The catch is that the Great Attractor lies in a direction where our view is obscured by the Milky Way itself. Peering outward from Earth, one part of the sky is crowded with the stars, gas, and dust of our own galaxy's disk. This murky zone blocks our view of what lies beyond it, hiding countless distant galaxies behind a veil. And it is precisely behind this veil, in the region astronomers quaintly call the zone of avoidance, that the Great Attractor resides. For a time, its presence was known only through its gravitational effects, a tug on our galaxy from behind the curtain of the Milky Way's stars. Over the years, astronomers have used indirect eyes to lift this veil. By scanning the area in radio waves and infrared light, which can penetrate the dust, they began to reveal what lurks there. They found clusters of galaxies in that hidden realm, many more galaxies than average, clumped together. One of them, known as the Norma cluster, is a massive collection of galaxies that appears to sit near the center of this gravitational focal point. The evidence suggests the Great Attractor is not a single object, but a dense region of the universe overflowing with galaxies and dark matter. It is like a huge gravitational basin, and our Milky Way is one of countless rivers of galaxies flowing into it. This finding added a new tier to our cosmic address. We knew that Earth orbits the Sun, which orbits the center of the Milky Way. We learned our galaxy is part of a small collection of galaxies, the local group, itself near a larger gathering, the Virgo cluster. Now, the Great Attractor revealed that even Virgo is just one section of an even larger entity, a colossal supercluster of galaxies. It was as if we had zoomed out and discovered that our galactic neighborhood is part of a city, and that city part of an entire country of galaxies. Our Milky Way resides on the outskirts of this vast supercluster that we are only beginning to chart. In 2014, scientists finally mapped out our larger cosmic neighborhood in unprecedented detail. They identified a gigantic supercluster of galaxies, of which the Great Attractor is the core, and named it Laniakea, meaning immense heaven in Hawaiian. Our Milky Way, the Andromeda Galaxy, and roughly 100,000 other galaxies are all part of this one titanic structure. Like dust motes caught in a vast eddy, we are drifting along the currents of Laniakea toward its center. The Great Attractor is essentially the heart of this immeasurably large gathering of matter. Its total mass has been estimated to be mind-boggling, on the order of 10 million billion suns, enough to bend the motions of galaxies across hundreds of millions of light years. Yet, even this may not be the final word. The Great Attractor itself appears to be moving, drawn onward by an even larger concentration of mass farther away, often called the Shapley supercluster. It seems our region of the cosmos is part of a chain of gravitational influences, where smaller groups fall into clusters, clusters fall into superclusters, and superclusters may be pulled toward even grander structures. In this hierarchy, the Great Attractor was our clue to the vast structure, Laniakea. And beyond Laniakea, there are hints of something more. The mystery, then, is not only what the Great Attractor is, but how it fits into the even larger tapestry of gravity in the universe. For now, what we know is that our galaxy and many others are on a slow collision course with the Great Attractor's realm. Though the expansion of the universe works against it, the local pull is strong enough that over billions of years, our local group may merge with the larger cluster at the Great Attractor's core. One day, eons from now, the Milky Way could become part of a massive cluster of galaxies there, bound together even as the rest of the universe recedes out of sight. It is a distant destiny, a gentle dance of galaxies drawn together by gravity's invisible hand, all orchestrated by this hidden mass we have only begun to chart. Light itself can be our guide to the unseen, just as gravity directs the motion of stars and galaxies. It also bends the very light those stars emit. According to Einstein's theory of relativity, a massive object warps the fabric of space around it, causing light from background objects to detour and curve. This phenomenon was dramatically confirmed in 1919 when a team of astronomers observed starlight bending around the sun during a solar eclipse, just as Einstein's new theory predicted. In the vast cosmos, this means that a massive galaxy or cluster can act like a lens for more distant galaxies behind it. The background galaxy's image is distorted by the gravity of the foreground mass, often stretched into arcs or even perfect rings of light. These ethereal rings and smears in the sky are known as gravitational lenses, nature's own magnifying glasses, highlighting the otherwise invisible influence of gravity. In some cases, gravity's lensing trick creates multiple images of the very same object. A famous example is the Einstein cross. A distant quasar, a brilliant beacon powered by a supermassive black hole in a young galaxy, appears in our sky as four identical points of light arranged in a cross around a foreground galaxy. In reality, those 4 points are all the same quasar, its light split into 4 paths by the precise alignment of an intervening galaxy's gravity. When this mirage was first discovered, it was a stunning confirmation of Einstein's prediction. Here was a single remote object, transformed into a celestial 4-leaf clover by the space-bending mass of another galaxy in between. Astronomers have turned these cosmic lenses into tools for discovery. By studying the warped light, they can map where unseen mass lies. In some cases, a foreground galaxy's visible matter alone cannot account for the precise shape of the lensed images. The light might be bent a bit too strongly, or split into an unexpected number of images. These anomalies hint that there is extra mass hiding in the lens, perhaps a halo of dark matter, or even an entire invisible galaxy. In fact, one spectacular lensing observation revealed a telltale quirk in an Einstein ring's shape. Upon investigation, it turned out a small dark galaxy, entirely unseen in any telescope, was lurking in the area, its gravity betraying its presence by subtly perturbing the ring of light. It's akin to noticing a flaw in a piece of glass by how it distorts the view through it. One scientist likened it to seeing raindrops on a window pane. You don't see the drops directly, but you see the way they bend and blur the scene behind the glass. Similarly, the otherwise invisible dark galaxy in that lensing system announced itself through the faint ripple it caused in the background galaxy's image. Such gravitational lensing anomalies are precious clues. They allow astronomers to detect and even weigh objects that emit no light, from sprawling dark matter halos to perhaps even rogue black holes or other exotic massive bodies, purely by the imprint their gravity leaves on passing starlight. Gravitational lensing has even provided some of the strongest evidence for dark matter's existence. In collisions of galaxy clusters, astronomers have observed that the mass mapped by gravitational lensing is offset from the hot gas visible in X-rays. The invisible mass, dark matter, cruised through the collision, while normal matter gas was left behind, separating the two. Such observations, only possible through the bending of light, offer a window into events and entities we cannot see directly. With each cosmic mirage we study, we peel back another layer of the cosmic mystery. Gravitational lensing, while pointing to invisible mass, also provides a powerful tool to study the universe. These natural lenses magnify and brighten the light of background galaxies, like a cosmic telescope built by gravity. Thanks to massive galaxy clusters acting as lenses, We have observed galaxies so distant and faint that they would normally be beyond our reach. Through these cosmic magnifying glasses, we glimpse the universe as it was in the remote past, seeing infant galaxies and stars. In this way, gravitational lensing not only reveals hidden matter, but also extends our vision, allowing us to explore deeper into space and time than ever before. Even on the scale of individual stars, gravity can play tricks with light. Astronomers sometimes witness a distant star momentarily brighten and then dim again over weeks, a phenomenon known as microlensing. It happens when a dim object, like a faint star or even a planet, drifts precisely in front of a background star. The foreground object's gravity bends and focuses the star's light just enough to make it appear briefly brighter. Such microlensing events have unveiled planets orbiting far-off stars, and even isolated rogue planets and black holes roaming the galaxy. Celestial bodies otherwise too dark to detect. It's another way the gravitational bending of starlight reveals the hidden denizens of space. Every arc of light, every distorted galaxy image, is like a whisper from the darkness, hinting at what lies hidden. Through gravitational lensing, we extend our vision beyond visible light, using gravity itself as a telescope. And yet, for all we glean from these tricks of light, countless questions remain. The more we uncover, dark matter holding galaxies, dark energy pushing the cosmos, vast voids, mysterious attractors, and lensing ghosts, the more we realize how much is left to understand. The universe communicates in subtle ways, through gentle tugs and faint flickers, inviting us to piece together its secrets. Our journey continues, slow and curious, further into the unknown, where new wonders surely await just beyond our sight. Beneath the familiar stars in the night sky lies a hidden cosmos, full of mysteries our eyes cannot see. In the stillness of space, unseen forces and structures shape the grand design of the universe. Tonight, we journey through these cosmic enigmas, beyond science, into realms of wonder and the unknown. Beneath the starlight of our galaxy, something invisible holds everything together. Each galaxy spins like a giant pinwheel of stars, and yet, without an unseen weight, those stars would fly off into the void. This missing weight is what we call dark matter, an invisible mass that neither shines nor reflects light. We cannot see it, but we feel its gravity. It surrounds and permeates galaxies like a gentle, binding glue. For decades, astronomers have noticed strange motions in space. The outer stars of galaxies orbit too fast, as if pulled by a hidden presence. Whole clusters of galaxies move in ways that defy the gravity of the visible stars alone. Something more is there, everywhere, in the dark. Dark matter makes up most of the mass in the universe. Picture an iceberg floating in the ocean. The bright tip that we see is the stars and glowing gas, but the vast bulk lies submerged and invisible beneath. This is dark matter. Though we cannot observe this cosmic scaffold directly, its influence is profound. Over billions of years, it helped shape a vast cosmic web, with galaxies forming along its filaments. In the early universe, dark matter's gravity guided the dance of creation. It drew in clouds of gas, shepherding them into clumps that became galaxies. Invisible halos of dark matter formed the framework, and luminous galaxies lit up like lanterns along those hidden scaffoldings. The largest structures we see, the clusters and superclusters of galaxies, are tied together by enormous webs of this unseen matter. Yet what exactly dark matter is remains unknown. It might be made of exotic particles that hardly ever touch ordinary matter. Scientists have built sensitive experiments deep underground and far in space to catch a glimpse of these ghostly particles. So far, they have come up empty-handed. Not a single spark of dark matter has directly lit up our detectors. The mystery endures. We see dark matter's pull on the cosmos, but the substance itself stays elusive. If you could hold out your hand in a dark, empty corner of space, countless dark matter particles would be streaming through it each second, yet you would never feel a thing. They slip through you and through Earth as though we weren't even here. They are like phantoms, present but untouchable. We know dark matter only by its gravity. Sometimes we catch it warping the light from distant galaxies. A massive, invisible halo can bend light like a lens, distorting a galaxy's image into smears and rings. In those ghostly rings of light, we see the fingerprint of dark matter, a hidden mass revealing itself by the way it curves spacetime. In one dramatic cosmic encounter, two huge clusters of galaxies crashed into each other. The hot gas in those clusters slammed together and slowed down, but their dark matter passed straight through, like spirits moving unhindered. Astronomers mapped the aftermath. The glowing X-ray gas was left behind, while the mass detected by gravitational lensing had moved on. The picture was clear. Dark matter separated from normal matter, each going its own way. It was a striking confirmation that this invisible mass is real and different from anything we can see. Still, the true nature of dark matter remains one of the greatest cosmic mysteries. It could be a new kind of particle, forged in the earliest moments of the Big Bang, drifting through space even now. It could be many things we have imagined, or something we haven't imagined at all. For now, we live with the questions. We look up at galaxies and know an invisible part of them is holding them together. Without dark matter, the stars would lose their anchor. With it, the cosmic dance goes on, guided by an unseen hand. While dark matter silently binds the universe together, another mysterious presence works in the opposite way. If dark matter is an invisible glue, then there is also an invisible push, one that is making the universe expand faster and faster, as if urging it to run away into the night. Out in the depths of space, galaxies are drifting apart, carried by the swelling expansion of the universe. And as if that weren't strange enough, this expansion is speeding up. There is a force, or something like a force, driving galaxies away from each other at an ever-growing pace. We call this mysterious influence dark energy. This phenomenon was a stunning revelation. Astronomers looking at distant exploding stars found they were dimmer than expected, meaning they were farther away than they should have been. The universe wasn't just expanding, it was accelerating, as if pushed by an unseen energy woven into the fabric of space itself. The discovery was like finding out that a gentle breeze had turned into a growing wind, carrying everything outward faster and faster. Dark energy is even more perplexing than dark matter. It doesn't gather in clumps or form halos around galaxies. Instead, It seems to be everywhere, evenly distributed through space, quietly making more space as the universe grows. Imagine the universe as a vast, stretching fabric. Dark energy is like a subtle pressure within that fabric, urging it to stretch ever more. As space expands, it appears that more dark energy emerges with it, fueling an accelerating cycle. By our best estimates, dark energy makes up nearly 70% of all the energy and matter in existence. Think about that. Most of the cosmos is this enigmatic expansionary energy. We can't see it or hold it, but its effect dominates the universe at the grandest scales. It's as though the cosmos has a secret heartbeat, a steady pulse that quickens the expansion with time. In the earlier days of the universe, gravity was in charge. After the Big Bang, the expansion was slowing down under gravity's pull. Galaxies were drawing on each other, and it seemed possible that the expansion might eventually halt or reverse. But a few billion years ago, the balance tipped. Dark energy grew to overshadow gravity on cosmic scales, and the expansion started to speed up. Now, with each passing eon, galaxies race away faster. The farther a galaxy is, the more swiftly it recedes, riding the accelerating flow of space. What exactly is dark energy? One idea is that it could be a built-in energy of empty space, what Einstein once called a cosmological constant. Empty space isn't truly empty. Even in a perfect vacuum, tiny quantum fluctuations dance in and out of existence. These might give space a sort of faint pressure that, when summed over the vastness of the universe, pushes everything apart. If that's true, then dark energy might be an ever-present property of the universe, the very fabric of space-time gently repelling itself. Yet this explanation raises as many questions as it answers. Our theories of quantum physics predict an unimaginably larger value for this vacuum energy than what we observe as dark energy. Why is the effect so subtle, just enough to gradually overtake gravity, rather than an immediate blast that would have torn everything apart? It's as if the universe tuned itself delicately, a whisper of energy that only became significant after billions of years. Other ideas suggest perhaps dark energy changes over time, or that it could be a new kind of field or force permeating space. Some even wonder if our understanding of gravity itself needs revision on the largest scales to account for the accelerating expansion. For now, these ideas remain speculative. We gather data, watching how the expansion rate might have changed over cosmic history, to see if dark energy is truly constant or if it evolves. New telescopes scan the light of distant galaxies and supernovae, acting as cosmic mileposts to map this acceleration. What we do know is that dark energy will shape the far future of the cosmos. If it stays as it is, or grows stronger, distant galaxies will slip beyond our horizon of sight. Trillions of years from now, an observer in our galaxy's future might see only darkness, as other galaxies rush out of view, carried away by the ever-accelerating expansion. The night sky, now speckled with countless galaxies through telescopes, would eventually become nearly empty. Here and now, dark energy doesn't affect our daily lives. Its push is incredibly gentle on smaller scales. Within our solar system, or even our galaxy, gravity reigns, and dark energy's effect is infinitesimal. But across the span between galaxies, over hundreds of millions of light years, that gentle push adds up to a powerful effect. It's a reminder that the universe can behave very differently on the largest scales than it does in our cosmic neighborhood. Dark energy remains a profound mystery. We named it, but naming a mystery is not the same as solving it. It is an answer that opens more questions. What is this vast, invisible energy field? Why does it exist? How does it fit into the tapestry of physics we know? As we ponder these questions, we continue to observe and imagine. As dark energy forces the cosmos outward, it also accentuates the great gaps in the cosmic landscape. Between the clusters of galaxies, the expanding universe leaves vast stretches nearly empty. Next, we drift into these silent voids, enormous cosmic cavities where nearly nothing resides, and see what secrets emptiness might hold. Now imagine drifting into a truly immense emptiness. In these cosmic voids, darkness and silence reign. If you were floating in the center of such a void, you might look out and see hardly any galaxies at all. The nearest galaxy could be tens of millions of light years away, or more. The usual bright tapestry of the cosmos would fade into a sparse scattering of faint, distant lights, and in every other direction, almost nothing, just blackness. Astronomers have found these vast voids while mapping galaxies across the universe. One of the largest, known as the Boötes void, astonished researchers when it was discovered. It spans roughly 330 million light-years in diameter, yet contains just a handful of galaxies. To picture that scale, a region of space so wide that thousands of galaxies could fit inside it, and yet only perhaps a few dozen are actually there. It's like a town that should have thousands of people, but instead has only a few lone souls. An emptiness so grand that it defies intuition. How do such enormous voids come to be? The clues lie in the way matter clustered over cosmic time. In the early universe, matter was distributed with slight unevenness. Some places a bit denser, some a bit emptier. Gravity pulled more strongly where there was more mass, drawing material in from the surroundings. As billions of years passed, the dense regions became denser, forming galaxies and clusters, while the less dense regions lost more and more matter, growing ever emptier. Small voids between galaxies merged into larger voids. Over time, this process sculpted a cosmic web, filaments and walls of galaxies surrounding cavernous voids. Think of soap bubbles packed together. Galaxies and clusters trace the thin walls of the bubbles, and the voids are like the hollow interiors. Our universe's large-scale structure resembles this foamy pattern. The Boötes void, for instance, is like a giant bubble that got blown extra large, with most of its content pushed to the edges. Inside a void, the environment is extremely lonely. A galaxy in such a void would be isolated, with minimal interaction or mergers to stir its stars. Its sky would lack the rich backdrop of other galaxies. Here on Earth, with powerful telescopes, we can see thousands of galaxies in various directions. But if we were in the middle of a huge void, even the most sensitive telescope might find only a few faint smudges of light on the horizon of space. The rest would be deep darkness. Voids aren't completely empty. There are stray atoms drifting, perhaps a tenuous wispy gas, and dark matter threading through, but at a fraction of the density found elsewhere. Occasionally a small galaxy or two might wander through, like a lost ship crossing an oceanic expanse. But by and large, these are the deserts of the cosmos. The existence of such great cosmic voids is both expected and intriguing. Our simulations of the universe's growth produce voids naturally, but when we actually observe one as vast as the Boötes void, it's still breathtaking. It makes us wonder, are there even larger voids out there, perhaps beyond our observable horizon? What might they tell us about the initial conditions of the universe? Scientists have even speculated that a huge void could be connected to unusual cold spots seen in the faint afterglow of the Big Bang, though this is still under debate. What voids teach us is the importance of nothingness in shaping something. Without voids, we wouldn't have the grand sheets and clusters of galaxies. The contrast between emptiness and matter is what outlines the cosmic landscape. The voids are like the dark valleys that make the bright mountains stand out on a relief map. Gliding through a cosmic void in our imagination, we feel a profound stillness. There is a subtle beauty in the idea of so much nothingness, a quiet counterpoint to the busy galaxies. In the darkness, one might feel truly alone, yet also witness the distant glimmer of entire galaxy superclusters far at the edges, like the lights of towns on a far horizon. Eventually, as we continue our journey, leaving the void, we enter regions where galaxies cluster again. And in those regions, we find another mystery. This time not an absence of matter, but perhaps an excess, or at least an unseen source of gravity. Imagine entire galaxies, including our own, moving on a grand scale towards something hidden, away from the emptiness of voids and back into the throng of galaxies. We sense a mysterious pull, a deep gravity well that beckons us. This leads us to the Great Attractor, a cryptic region that seems to be drawing us in with a gravitational force we can't yet fully map. Far away, in the direction of the constellation Centaurus, lies a mystery that tugs on our entire galactic neighborhood. In the late 20th century, astronomers mapping the movements of galaxies noticed something curious. The Milky Way, Andromeda, and thousands of other galaxies around us are all drifting toward a particular patch of sky. They're moving at an astonishing speed, on the order of hundreds of kilometers per second, drawn by the gravity of something immense and largely unseen. This enigmatic puller of galaxies was dubbed the Great Attractor. Imagine a gentle but vast gravitational current, like an undertow in the ocean, steadily drawing everything in a certain region towards one point. We don't notice it in everyday life, but on a cosmic scale, our whole local group of galaxies is being carried along by this current. It's as if space itself has a subtle slope in that direction, and we are rolling downhill without knowing where the slope leads. Why is the Great Attractor so hard to see? Part of the answer is that our own Milky Way is in the way. The region of the sky where this pull comes from is heavily obscured by the Milky Way's stars, gas, and dust, an area astronomers poetically call the zone of avoidance, because it's so difficult to observe beyond our galaxy's plane. Peering through this veil with visible light is almost impossible, but with radio and infrared observations, scientists have found hints of large clusters of galaxies hiding behind the dust. These clusters, and perhaps even bigger conglomerations beyond, are thought to be the source of the Great Attractor's gravity. Over time, as our observational tools improved, we've mapped more of what lies in that direction. It appears that the Great Attractor is not a single object, but a region of enhanced mass, a combination of groups and clusters of galaxies. One major component is the Norma cluster, a massive cluster of galaxies relatively nearby, in cosmic terms. And even beyond that, further out, lies an even more massive collection called the Shapley supercluster. In fact, our Milky Way and its neighbours are part of a titanic structure of galaxies known as the Laniakea supercluster, which spreads out over 500 million light-years. The Great Attractor can be thought of as the gravitational centre of Laniakea, the point toward which much of this supercluster's content is flowing. It's humbling to realise that while we orbit the centre of our galaxy, and our galaxy moves within its local cluster, the cluster itself is involved in an even larger dance. We are passengers on a very slow journey toward the great attractor, a journey that will take billions of years. The speed may sound extreme, around 1,000,000 miles per hour, but over the vast distances of space, this drift won't cause dramatic changes anytime soon. Still, it reveals that the universe has currents and eddies. Not everything is just expanding uniformly outward. There are local motions on top of the expansion, caused by uneven distribution of mass. The great attractor's pull is a testament to the influence of gravity on enormous scales. Just as dark matter's gravity holds galaxies together, and just as voids result from matter moving away, here we have a case of galaxies moving en masse toward a giant hidden mass concentration. It shows us that even in our relatively nearby extragalactic neighborhood, there are still things we hadn't seen directly, but could infer from their effects. There is also a poetic aspect to this. We are being pulled towards something we cannot see. It reminds us of how much remains hidden in the cosmos. Only by its tug on our galaxy do we know the great attractor is there, much like sensing a presence in the dark by the way it moves the air around us. Scientists continue to study this region with advanced observatories, trying to catalogue every galaxy and cluster that might be part of this great gravitational anomaly. With X-ray telescopes, they find hot gas in massive clusters, and with new surveys, they trace the patterns of galaxy flows. Piece by piece, the once mysterious great attractor is becoming more understood, likely an amalgam of several galactic superstructures rather than some singular exotic object. Even so, the name Great Attractor captures our imagination. One can't help but picture a massive unseen vortex pulling cosmic islands inward. In truth, it won't suck us in like a drain. Space is expanding too, and this is a slow rearrangement of clusters over eons. But the concept that our galaxy is on a journey we never knew about until recently is mesmerizing. Having explored an unseen pull that guides our galaxy's path, we turn to another way. Gravity reveals the invisible. Instead of dragging whole galaxies around, gravity can also bend the very light that reaches us. In the next part of our journey, we search for clues in the distortion of starlight itself. The phenomenon of gravitational lensing often uncovers hidden mass, and sometimes it presents anomalies that leave astronomers scratching their heads. Through these warped and magnified visions of distant galaxies, we find new hints of the unseen cosmic web. High above Earth's atmosphere, telescopes gaze at distant galaxies and sometimes witness a breathtaking sight. Rings and arcs of light wrapped around closer galaxies or clusters. These are not actual physical rings, but the stretched and magnified images of even more distant galaxies located behind massive objects. Gravity, as Einstein revealed, can bend the path of light, and in doing so, massive objects act like cosmic lenses. This phenomenon, known as gravitational lensing, often creates multiple images of a single background object or smears its light into curious shapes. It's like nature's own kaleidoscope, a beautiful consequence of gravity's influence on light. One of the most striking examples is an Einstein ring. If a distant galaxy aligns just right behind a nearer galaxy, its light can be bent into a perfect or near-perfect circle around the foreground galaxy. We see a glowing band or ring that is actually the distorted image of the far-off galaxy. More commonly, we see arcs or multiple separate images. A famous case is the Einstein cross, where a distant quasar appears as four symmetrically placed dots of light around a foreground galaxy. Four images of the same object, created by the warp of spacetime. These cosmic lenses are more than just visual oddities. They are tools for discovery. By studying how the light is distorted, scientists can infer the mass of the object doing the lensing, even if much of that mass is invisible dark matter. In fact, gravitational lensing has been one of the key methods to map the distribution of dark matter in clusters of galaxies. Where the visible matter isn't enough to account for the lensing pattern, we know dark matter must be present to supply the extra gravity. However, every now and then, gravitational lensing presents puzzles. Sometimes the lensed images are not quite where or how bright we expect them to be. These anomalies can be subtle. Perhaps one of the 4 quasar images in a lens is dimmer than the others, or an arc is a bit twisted compared to models. Such discrepancies hint that we might be missing some pieces in our understanding of the mass in the lens. One possibility is that there are small clumps of dark matter, or even unseen objects, like rogue planets or black holes, along the line of sight that further perturb the light. Imagine a pristine sheet of glass with a small chip or ripple. The image seen through it might have tiny distortions. Similarly, a little clump of mass can slightly alter one portion of a lensed image. Astronomers call these flux anomalies or lensing anomalies, and they often use them to infer the presence of otherwise undetectable mass concentrations. In some strongly lensed systems, the only way to explain the odd brightness pattern of multiple images is to assume an extra invisible mass, perhaps a dwarf galaxy or a dark matter clump lying near one of the light paths. On the largest scales, studies of cluster lenses, massive clusters lensing background galaxies, have revealed more detailed distortions than originally anticipated. It's as though the cluster's mass distribution is clumpier on small scales than our simulations might predict. This has sparked discussions. It could mean that clusters have many small sub-halos of dark matter, essentially numerous mini-clusters within them. Or it could hint that our model of dark matter, often assumed to be smoothly distributed aside from big clumps, might need refinement. Every such lensing observation provides data to test our theories of how dark matter behaves. Gravitational lensing isn't only about distant galaxies and quasars. It happens on smaller scales too, in what we call microlensing. Imagine a single star in our galaxy brightening for a few weeks or months, then returning to normal. If we rule out the star having an intrinsic flare, the likely cause is a massive but invisible object passing exactly between that star and us. It's gravity focusing the star's light toward Earth for a time. This is gravitational lensing on a star-by-star basis, and it has been used to discover planets orbiting distant stars and even isolated black holes wandering the galaxy. In fact, some of the first microlensing surveys were set up to test if dark matter could be hidden in the form of many faint stars or black holes, so-called machos. They detected some microlensing events, but not enough to account for dark matter. Still, these experiments led to surprises. They have found Jupiter-sized planets drifting free in space, not bound to any star, detected only because their gravity momentarily magnified the light of a background star. And recently, astronomers caught what appears to be a lone, stellar mass black hole, invisible on its own, revealing itself by the way it made a background star's light temporarily surge and shift. It's awe-inspiring. A black hole that would normally be undetectable becomes known to us purely through its effect on starlight, like a ghost leaving a brief footprint. Each lensing event, whether a dramatic Einstein ring or a subtle flicker of a star, is a clue, a message carried by light across space and bent en route. Through these clues, we piece together where unseen mass resides. And in those cases where the light's message doesn't fit our expectations, we find hints that the cosmic game might be more complex than we thought. Do these gravitational lensing anomalies point to new physics? Or are they simply telling us that the universe has a lot of small, dim structures, like tiny galaxies or clumps of dark matter, that we've yet to catalogue? The jury is still out. But it's a beautiful synergy of art and science that by studying the graceful arcs and rings in the sky, we can uncover hidden truths about the cosmos. As we sift through these distorted images and puzzling clues, we sometimes discover entire galaxies that themselves seem out of place in our theories. In fact, while mapping dark matter and stars, astronomers have identified galaxies that defy the normal expectations, some with hardly any dark matter where we expect lots, and others that appear to be mostly dark matter with very few stars. These phantom galaxies stand as new riddles. Let's journey next to explore these unusual galaxies, which challenge what we thought we knew about how galaxies form and hold themselves together. Galaxies, in general, are thought to obey a common recipe. A hefty dark matter halo holds everything together, and within it, gas cools and forms stars. Typically, the invisible mass outweighs the visible stars by a large factor. That's why it was so startling when astronomers discovered galaxies that seemed to break this rule. These could be called phantom galaxies. They either lack the dark matter glue we expect, or they are almost nothing but dark matter, with only a trace of stars. Both scenarios were once thought nearly impossible. Consider the case of a ghostly galaxy catalogued as NGC 1052 DF2. It's an extended smear of stars, so sparse that other galaxies can be seen right through it. When scientists measured the speeds of star clusters within this diffuse galaxy, they were astonished. The stars were moving slowly, just as you'd expect if they felt the gravity of only the stars and not much else. In other words, unlike every other galaxy of its size, DF2 didn't seem to hide a big pocket of dark matter. It was as if the invisible foundation was missing. What you see is truly what you get. Initially, some wondered if there was a mistake. Perhaps the galaxy was closer than assumed, which would make its mass calculations different. But further careful measurements confirmed its distance and the original result. This galaxy has an extremely low dark matter content. How could a galaxy form without dark matter? It's a conundrum. One idea is that it did have a dark matter halo originally, but an interaction with another galaxy stripped it away. Imagine a small galaxy venturing too close to a larger one. The tidal forces could pull the dark matter, and some stars, out, like taffy stretched apart, leaving a tenuous remnant behind. Another possibility is that this galaxy is the product of several smaller galaxies merging in just the right way to end up with mostly stars in the center and dark matter flung outward or lost. Or perhaps it formed in a unique corner of the universe where conditions somehow led to a shortage of dark matter from the start. For now, we don't have a definitive answer. We only know such galaxies exist, and they challenge our understanding. Not long after the discovery of DF2, another similar galaxy, NGC 1052 DF4, was found in the same region, also deficient in dark matter. Finding a second example strengthened the case that we're looking at a real phenomenon and not an observational fluke. These galaxies are large in size, but incredibly low in density, sometimes called ultra-diffuse galaxies. They've been described as see-through or cotton candy galaxies due to their gossamer appearance. It's poetic that something so diaphanous and delicate-looking would also be the one galaxy type missing the heavy dark matter that usually anchors galaxies. On the flip side of the phantom coin are galaxies that are practically nothing but dark matter. These are objects where the stars are few, but the mass is great. An example emerged a few years earlier in the Coma cluster of galaxies. a faint, diffuse object designated Dragonfly 44. Through a large telescope, Dragonfly 44 appears as a dim blob, barely distinguishable from the background. It has only a tiny fraction of the stars our Milky Way has. Yet measurements indicated it might have a mass almost as large as the Milky Way's. If true, that means over 99% of that galaxy's mass is invisible. Imagine a massive platform of dark matter, and on it only a sprinkling of stars. A structure that by all rights could have been a majestic galaxy, but somehow failed to ignite with starlight. Astronomers have given colourful nicknames to these sorts of objects. Some call them dark galaxies, or almost dark galaxies. In some cases, they detect them by the presence of hydrogen gas rotating as if in a galaxy, but with hardly any starlight. These might be galaxies that never got a chance to form many stars, perhaps because their gas was blown out by radiation or stripped by nearby clusters. They are like cosmic embryos that never fully developed, leaving a ghost outline of what a galaxy could have been. Both types of phantom galaxies, the ones missing dark matter and the ones missing normal matter, are telling us that the formation and evolution of galaxies is a more eccentric story than we assumed. It appears that under certain circumstances, the usual balance between dark and light, unseen and seen matter, can be skewed dramatically. Each discovery of an oddball galaxy sends theorists back to the drawing board. Can our models accommodate this? Can a simulation produce a galaxy with almost no dark matter, or one with almost no stars? If so, what special conditions are required? If not, what are we missing? These discoveries also excite those who propose alternatives to dark matter. If, for instance, some modification of gravity is the true cause of galaxy rotations instead of dark matter, then a galaxy without dark matter would be a critical test. So far, even modified gravity theories have a hard time explaining an object like DF2, which seems to behave exactly as if only normal matter is present. It's as though nature set up a controlled experiment for us. Here's a galaxy without dark matter. Figure it out. In the end, phantom galaxies remind us that the universe still holds surprises on every scale. We thought we had a decent grasp on how galaxies work, yet these ethereal outliers tell us there's more to learn. They spark new questions. Did we perhaps overlook a process that can separate dark matter from galaxies? Could dark matter have different types or states, where occasionally it doesn't clump with gas and stars? Or are these spectres simply rare outcomes of cosmic accidents, the eccentric cousins of typical galaxies? As we ponder these questions, our journey now shifts perspective. We have been looking at grand structures and unseen forces shaping the cosmos. But to truly delve into the unknown, we might need to go deeper, down to the very fabric of reality. The answers to dark matter, dark energy, and the behavior of the cosmos may well hide in the quantum realm, the domain of the very small that governed the universe at its birth. Now we turn to a new perspective, listening for quantum echoes in space, subtle hints that the tiny and the immense are intertwined in ways we are just beginning to fathom. We now dive beneath the grand scale of galaxies and clusters, down to the very underpinnings of reality, where another kind of mystery lies. The world of the very small, the quantum realm, might seem far removed from the cosmic expanse. But in truth, the earliest moments of the universe were ruled by quantum forces. In those first fractions of a second after the Big Bang, the entire cosmos was smaller than an atom, a hot sea of quantum particles and fields. Tiny, random fluctuations flickered in that primeval chaos. As the universe expanded and cooled, those infinitesimal ripples were stretched out, eventually becoming the seeds of galaxies and clusters. In a very real sense, every galaxy that shines in the night sky can trace its origins to a quantum whisper in the dawn of time. We can still observe an echo of that era, the cosmic microwave background, a faint afterglow of the Big Bang that bathes the universe. If you look closely at this all-sky glow, with sensitive instruments of course, it isn't perfectly uniform. It has tiny variations in temperature, like faint freckles across the sky. These speckles are the direct imprint of those ancient quantum fluctuations, spots that were ever so slightly denser or hotter and later grew into the large-scale structure we see today. When we map the cosmic microwave background, we are essentially seeing quantum echoes writ large across the heavens. This idea is breathtaking, that the clustering of galaxies, the locations of great voids and superclusters, all follow a blueprint laid out by subatomic jitters billions of years ago. It's as if the universe carries a memory of its quantum infancy. The echoes of that time are subtle, but they surround us. Every time we gaze at the cosmic web of galaxies stretching across billions of light years, we're indirectly witnessing the outcome of quantum events at the universe's birth. Quantum physics also tells us that even what we call empty space isn't truly empty. The vacuum teems with ephemeral particles popping in and out of existence, a restless foam of existence at the smallest scales. Normally, these effects are vanishingly small and transient, but spread over the vastness of space, could they cumulatively have an effect? Some scientists suspect that dark energy might be connected to this vacuum energy, an accumulated push from those tiny fluctuations. The numbers don't neatly match up. Our current theories overestimate the effect by a staggering amount, but the concept hints that solving the dark energy mystery may require a quantum perspective on space itself. There are other tantalizing intersections of the quantum and the cosmic. Take black holes, for example. Titanic concentrations of mass, where gravity is so strong that not even light can escape. For a long time, they were thought to be truly black, nothing coming out once something falls in. But then quantum theory entered the scene. Stephen Hawking predicted that black holes aren't completely silent. They emit a faint thermal glow due to quantum effects at their boundaries. Over inconceivably long times, a black hole can evaporate via this Hawking radiation. This idea merges the world of enormous gravity with the world of tiny particles and fields. It suggests that even the most massive, star-swallowing void must bow to the laws of quantum physics in the end. A black hole might take eons to evaporate, but the fact that it would eventually vanish, leaking away its mass bit by bit as ghostly particles, is a profound clue. It tells us that quantum mechanics and gravity are intertwined, even if we don't yet have a full theory of quantum gravity to describe their union. Another conundrum lies in what happens to information in a black hole. Quantum physics insists information can't be destroyed, while a naive view of a black hole says anything that falls in is lost forever. Physicists suspect that a deeper quantum theory of gravity will resolve this paradox, perhaps by encoding that information in subtle correlations in the Hawking radiation, a sort of quantum echo of everything the black hole ever swallowed. It's a mystery still, but it shows how the questions of the ultra-small can echo at the scale of galaxies and beyond. Everywhere we look, we find that understanding the universe at large might require understanding the universe at its most microscopic. Dark matter itself could be a new kind of quantum particle, eluding detection because it interacts so weakly. Physicists around the world are trying to produce or capture such particles in high-energy experiments and dedicated detectors. If they succeed, we would be witnessing a quantum process in the laboratory that answers a cosmic question. What is the invisible mass holding galaxies together? Likewise, cracking the secret of dark energy might demand a theory that unifies quantum mechanics with our theory of space and time, general relativity. We have superb theories that separately describe atoms and describe galaxies, but they don't fully agree with each other in extreme conditions. Bridging that gap is one of the greatest scientific quests of our time. Some proposed theories, like string theory or loop quantum gravity, attempt to describe a quantum fabric of space-time, where space and time themselves have an elementary structure. So far, these ideas remain speculative, but perhaps the cosmos offers hints, subtle signatures in the cosmic background radiation, or patterns in the distribution of matter that could guide us toward the right path. Even the phenomenon of entanglement, that spooky quantum connection between particles, has cosmic implications. In recent experiments, scientists used light from distant stars to help ensure that entangled particles' choices were truly random and separated by cosmic distances, closing loopholes in tests of quantum theory. And some thinkers have imagined that maybe, just maybe, distant parts of the universe could be entangled in ways we don't yet perceive, or that wormholes, hypothetical bridges in space-time, might be a macroscopic manifestation of entangled states. These ideas blur the line between science fact and science fiction, but they underscore a common theme. The universe is a unified whole, and the micro and macro are deeply connected. As our journey through these mysteries comes to a pause for now, we're left with a sense of awe. We've wandered from invisible matter, holding galaxies together, to the accelerating stretch of space, through enormous voids of nothingness and unseen engines of gravity, past ghostly galaxies and into the subatomic tremors that underlie it all. Through it all, a thread connects each mystery. There is more than meets the eye, more than our current science can fully explain. Yet, humanity keeps searching, peering through telescopes, running particle colliders, thinking and dreaming. Under the quiet night sky, it's humbling and soothing to remember that it's okay not to have all the answers. The cosmos keeps its secrets well, but each mystery we've explored fuels our imagination. We picture dark matter particles dancing around us unnoticed, dark energy slowly propelling galaxies apart, vast voids where a traveller would find solitude for eons, and quantum flickers that set it all in motion. We feel the pull of the unknown, and rather than fear it, we find it beautiful. Our exploration is far from over. As we continue to gaze upward and also delve inward into the heart of matter, we carry the hope that one day the darkness will yield to understanding. Until then, we find comfort and wonder in the questions themselves, drifting in the cosmic ocean, listening to the faint echoes that hint at truths beyond our horizon. In the quiet depths of the night sky, mysteries flicker and call out across the vastness of space. We continue our journey beyond the known, now turning our gaze to the heavens themselves, to strange cosmic signals and uncanny phenomena that scientists are only beginning to grasp. From sudden flashes of radio energy that light up the sky for an eye blink, to eerie cosmic beacons and stars that defy expectations. These celestial enigmas invite us to listen, observe, and wonder. With a calm mind and a sense of awe, let us drift deeper into the cosmos, exploring phenomena that remain beyond science's full explanation. Imagine a telescope attuned to invisible radio waves, scanning the sky's silence, when out of the blue, a powerful burst of radio energy arrives, lasting barely a millisecond. It's as if the cosmos itself winked at us with a brilliant flash of radio light. Astronomers call these events fast radio bursts, and they are among the most perplexing signals we've ever intercepted. Each one is incredibly brief, often only a fraction of a thousandth of a second. Yet in that moment, it can unleash as much energy as our sun radiates in 3 entire days. These bursts are fast, and they are bright. But what makes them truly mysterious is that we still don't know what causes them. The first fast radio burst on record was discovered almost by accident. In 2007, a scientist named Duncan Lorimer and his student were combing through old telescope data when they spotted an intense, sudden signal that had been recorded years earlier. This was the inaugural flash, later nicknamed the Lorimer burst, and it appeared to come from billions of light years away. At first, such a brief spike of radio waves seemed almost too strange to be real. Could it have been just a glitch in the data, or perhaps some interference from Earth? But as researchers looked closer and started watching the skies in real time, more of these fleeting bursts began to show up. They were not illusions at all. They were a new cosmic phenomenon revealing itself. Fast radio bursts, or FRBs, now number in the hundreds. They arrive from all over the sky, random and unpredictable, each one a split-second flash from far beyond our own galaxy. Most appear to come from distant galaxies, millions or even billions of light years away. At that distance, to be detectable here, the burst must be astonishingly energetic at its source. Indeed, FRBs reach Earth with only a whisper of their original power. By the time they get here, their signal has been described as thousands of times weaker than a mobile phone signal would be if it were coming from the moon. Yet what we do detect is enough to tell us that the original burst was profoundly powerful. With each detection, radio telescopes record a characteristic sweep in frequency, lower-pitched radio waves arriving slightly later than higher-pitched ones. A telltale dispersion effect caused by the burst traveling billions of light years through intergalactic plasma. This means these flashes are not local at all. They truly hail from the depths of space. One by one, astronomers catalogued these bursts. Some were found only after the fact, hidden in archival data, while others have been caught live as they happened. For a long while, each FRB seemed to be a one-off event, a burst here, a burst there, never repeating. This only deepened the mystery. If these were cataclysmic events, the kind that destroy their source, one might expect them to occur just once. Each new detection felt like a solitary cosmic firework, leaving us wondering what set it off. But then, to everyone's surprise, a fast radio burst was discovered that did repeat. In 2012, one particular source was heard bursting again and again. This repeater, later pinpointed to a small dwarf galaxy about 3 billion light-years away, showed that whatever was causing those bursts wasn't destroyed by the first flash. It kept on flashing sporadically, as if some cosmic engine were revving intermittently. Stranger still, astronomers eventually found an FRB that follows a regular rhythm, a burst every 16 days or so. Such periodicity hints at an object in a cosmic dance, perhaps a rotating magnetized star or an orbiting system, acting like a lighthouse beam swinging by periodically. It was a precious clue, yet the full picture remained elusive. What could possibly create an FRB? Over time, investigators have proposed many ideas. The leading suspects are some of the universe's most extreme objects. Imagine a neutron star, the ultra-dense, collapsed core left behind when a massive star explodes. Now imagine one with an unimaginably strong magnetic field, a magnetar. Magnetars are prone to sudden, colossal flares. In 2020, such a flare from a known magnetar in our own Milky Way was detected as a fast radio burst. This was a breakthrough. It proved that magnetars can produce FRB-like signals. Perhaps many distant FRBs are caused by similar starquakes or eruptions on magnetars, each releasing a tremendous burst of radio energy that momentarily outshines whole galaxies. Other hypotheses range from the dramatic, two neutron stars spiraling into each other and merging in a flash, or a black hole's surface tearing material off a star, to the truly exotic, like the idea of cosmic strings, hypothetical tearings in spacetime, snapping and radiating energy, or even the notion of an alien civilization's technology leaking radio bursts into space. Yes, the idea of extraterrestrial intelligence has been whispered in the FRB discussion. It's a speculative thought, born from the sheer surprise these bursts caused. In science, when faced with an utter mystery, one keeps an open mind. However, as more evidence has accumulated, natural origins like magnetars have become the frontrunners, and there's no indication that FRBs are alien messages. But the diversity and unpredictability of these bursts remind us how much we still have to learn. As radio dishes around the world, and even in space, continue to listen, the story of FRBs is still unfolding. New bursts are now detected frequently. In one recent campaign, over 500 bursts were spotted in just a single year by a Canadian radio telescope array. Each one adds another data point to the puzzle. We've learned that some bursts are highly polarized, meaning the waves vibrate chiefly in one direction, a sign that they're born in extremely strong magnetic fields. We've identified host galaxies for a few. Some FRBs come from tiny star-forming dwarf galaxies, while others originate in big, mature galaxies, suggesting there might be multiple ways to light these radio flashbulbs. And still, every time an FRB arrives, it's as if a cosmic alarm bell rings for but an instant, then fades back into silence. The sudden flash, and then the mystery of its origin, can leave even the most seasoned astronomer in awe. For now, fast radio bursts remain a vivid example of how little we truly understand about the goings-on in our universe. They flash and vanish, reminding us that out there in the dark, energetic events are happening that we've never imagined. Under the tranquil sky, our radio ears will keep listening, hopeful for each new burst, each one a potential clue. And perhaps, in time, we will decipher the message these fleeting cosmic sparks are sending. Not all of the strange signals we've stumbled upon are so fleeting as those fast radio flashes. Some have been singular events, one-time cosmic whispers that came without warning and haven't been heard again, yet left us with enduring questions. One such case has passed into legend among astronomers. It's known simply as the WOW signal. Where FRBs are like brief, repeating flickers, the WOW signal was more like a solitary beacon, a cosmic shout from the darkness, heard just once on a late summer night in 1977. Late one August evening in 1977, at an observatory in Ohio, a giant ear was listening to the stars. This was the Big Ear radio telescope, quietly surveying the sky in the constellation Sagittarius as part of a long-running search for extraterrestrial signals. For years, Big Ear had heard nothing unexpected, just the background hiss of celestial radio noise. But on this night, something extraordinary happened. The telescope recorded a sudden, intense radio signal, unlike any it had picked up before. It was a narrow-band signal, concentrated at a very specific frequency, and it was extremely strong. By all appearances, it bore the hallmarks of what scientists expected a deliberate broadcast from an alien civilization might look like. When the data was reviewed a few days later, astronomer Jerry Ayman couldn't believe his eyes. On the printout of the telescope's readings, a particular sequence of characters jumped out: 6EQUU5. This string represented the signal's intensity over time, and one value in it, corresponding to the letter U, was off the charts. In the system used, U meant the signal was 30 standard deviations above the background noise level. In plain terms, it was a massive spike. Startled and excited, Ayman grabbed a red pen and drew a circle around those alphanumeric digits, and in the margin, he scribbled one word: "Wow." That spontaneous exclamation became the signal's nickname. To this day, the original printout with "Wow" written beside the data remains an iconic artifact of one of the biggest cosmic mysteries. The "Wow" signal lasted for the full 72 seconds that Big Ear was pointed at that region of the sky. During that window, the signal rose and fell in intensity in a way consistent with the Earth's rotation, carrying the telescope beam across a distant radio source. Then, as the cosmos kept moving, the signal disappeared. In those 72 seconds, it didn't repeat or send any obvious pattern. It was just there, strongly, and then gone. Naturally, after this discovery, astronomers aimed other telescopes at the same patch of sky in Sagittarius, hoping to catch it again. They listened for days, then months, then years, but it never came back. The "Wow" signal was a one-time cosmic serenade. Because it never repeated, it left us unable to verify its source, hanging as an unresolved question mark in the annals of SETI, Search for Extraterrestrial Intelligence. What made the "Wow" signal so compelling was how perfectly it fit certain criteria scientists had dreamed of. It was narrow in bandwidth, meaning it wasn't spread across frequencies like natural static, but concentrated, as a communication might be. It was right around 1,420 MHz, the natural emission frequency of hydrogen, the most common element in the universe. Ever since the 1960s, some astronomers had mused that if aliens tried to get our attention, they might broadcast at or near the hydrogen line, since it's a universal reference known to any advanced science. And it came from the direction of Sagittarius, from no known Earth satellites or human transmitters. All checks for terrestrial interference turned up empty. In short, it looked exactly like how one might imagine an intentional interstellar beacon. No wonder Ayman and his colleagues were astonished. For a while, excitement bubbled up. Could this be it? The long-awaited signal from another civilization? In the community of scientists listening for voices from the stars, this was the most tantalizing moment they had ever experienced. Yet, science demands caution. Over the years since 1977, numerous hypotheses have been put forward to explain the "Wow" signal without invoking aliens. Could it have been a stray broadcast from an Earth satellite that just happened to mimic an extraterrestrial signal? Or perhaps a glitch in the equipment, or an undiscovered natural radio source in space? Every mundane explanation has run into problems. If it were a satellite, why was it never detected before or after? And why was it transmitting on a protected frequency band used for astronomy? If it was a one-time equipment glitch, it was uncannily specific, and nothing like it has been seen since. One astronomer suggested it might have been a passing comet with a cloud of hydrogen gas around it, radiating at just the right frequency. But when this idea was tested, it fell short. The comets in question weren't in the right position at the right time, and comets don't emit radio waves that strong at that frequency. In fact, in 2024, a team of researchers revisited the "Wow" signal with new observations and proposed that it could have been caused by a natural astrophysical event. Perhaps the energetic outburst of a star stimulating a cold hydrogen cloud, causing that cloud to momentarily shine in radio waves. This explanation, while intriguing, is still just an idea. It would have been a very rare event, something we haven't seen before or since. And thus the mystery endures, awaiting more evidence. And so the wow signal remains, to this day, an unsolved mystery. It was humanity's closest brush with what could be interpreted as an alien hello. And even though we cannot confirm that, we also cannot firmly rule it out. Jerry Amon himself, the man who wrote Wow, was always somewhat skeptical that it was truly a message from ET. He hoped that someday a more ordinary explanation would be found. But the fact is, decades later, no fully satisfying explanation exists. The part of the sky that cried wow at us has been quiet ever since. Whether the signal was a unique natural cosmic fluke or a genuine attempt at contact, it taught us something profound. That extraordinary signals are out there, hidden in the noise, waiting to be noticed. It reminds us to keep listening. Any day, on any quiet night, another wow could zip through our antennas without warning, and we wouldn't want to miss it. While the wow signal was a mysterious voice from the sky, other perplexing phenomena have been discovered by watching the light of distant stars. Our next cosmic enigma came not as a burst or a transmission, but as an uncanny dimming of starlight, a star that behaves like no other, growing fainter and brighter in ways we struggle to explain. In 2015, a team of citizen scientists and astronomers noticed something bizarre in data from NASA's Kepler Space Telescope. One particular star, catalogued rather unassumingly as KIC 8462852, suddenly became famous under a new name, Tabby's star. This star was flickering in a way that defied all expectations. Kepler's mission was to find planets around other stars by watching for tiny, regular dips in a star's brightness when an orbiting planet passes in front of it. Those dips are usually very slight, often less than 1% of the star's light, and they occur like clockwork every time the planet goes around. But Tabby's star was doing something entirely different. Its light was dipping by enormous amounts, sometimes plunges of 15 or even 20%, and these dimming events were irregular, with no clear periodic pattern. For context, even a giant Jupiter-sized planet transiting a star would dim it by only a couple of percent at most, and it would be on a fixed schedule. Yet here was a star that occasionally was losing a fifth of its brightness for days at a time, then returning to normal. Imagine watching a lighthouse whose beam suddenly dims by a fifth, then returns to normal, then later flickers out in some other odd pattern with no set schedule. That's what was happening 1,500 light-years away with this star in the constellation Cygnus. The volunteers who first spotted it were so perplexed that the scientific paper announcing the discovery had the tongue-in-cheek subtitle, "Where's the flux?" A nod to the WTF exclamation, hence the nickname WTF star for Where's the Flux. The star was nicknamed Tabby's star after Tabitha Boyajian, the lead astronomer who studied it and brought it to the world's attention. Naturally, once this discovery broke, it captured imaginations everywhere. What could cause such dramatic and strange dimming? Initial speculation focused on natural explanations. Perhaps a whole swarm of comets had disintegrated, creating a thick cloud of dust and debris that occasionally blocked the star's light. Or perhaps we were seeing the aftermath of some giant collision in that star system, throwing up an irregular veil of dust that sometimes drifts in front of the star. Another idea. Maybe the star was surrounded by a warped ring of dust or debris, perhaps left over from a destroyed planet or moon, causing intermittent eclipses. Yet no single hypothesis neatly explained all the observed quirks. The dimmings were not symmetrical or evenly spaced. Some were steep drop-offs, others more gradual. Some lasted just a day or two, others weeks. And perplexingly, over the 4 years that Kepler watched, Tabby's star not only dipped occasionally, it also seemed to be gradually fading in overall brightness, as if, on average, the light was being slowly throttled down over time. That long-term fading was contested at first, because it's hard to confirm from just a few years of data. But later studies of old photographic plates suggested the star might indeed have faded over a century as well. Something unusual was going on. In the absence of a clear natural explanation, a more fantastic idea inevitably emerged. Could it be that we were witnessing something akin to science fiction? The work of an advanced alien civilization? One hypothesis that caught the public's attention was that perhaps we were seeing a giant alien megastructure orbiting the star. Imagine a colossal assembly, often envisioned as swarms of solar panels or a huge partial Dyson sphere, built to capture the star's energy, occasionally blocking the light as it rotates or reconfigures. It was a wild notion, and scientists treated it as a very remote possibility, but it shows how exceptional Tabby's star appeared. People were grasping for any explanation, even alien astroengineering, to make sense of it. Researchers were quick to point out problems with the alien megastructure idea. For one, if something as enormous as a megastructure were blocking the star, you might expect it to re-radiate the star's light as heat, since no structure is 100% efficient. But follow-up observations with infrared telescopes didn't see the excess infrared glow that would likely accompany, say, a swarm of giant solar collectors absorbing starlight. The star's color and spectrum during the dips also didn't look like a clean, opaque object was cutting out the light completely. It looked more consistent with a translucent dust cloud. Astronomers worldwide turned their telescopes toward Tabby's star, observing it in many wavelengths and waiting to catch new dimming events in real time. Over the years, a consensus began to lean toward dust as the culprit, not a single solid object, but lots of tiny particles. The key clue was that the star's dimming was wavelength dependent. The star faded more in blue light than in red during its dips. That's exactly what you'd expect if a cloud of fine dust were partially blocking the star. Small dust grains scatter blue light more effectively than red. Perhaps a giant, uneven ring of dust or debris orbits the star, and clumps in this ring occasionally drift in front of the star, causing those big dips. In September 2019, one team of researchers suggested that the debris from the destruction of a large exomoon, basically a moon that got knocked out of its orbit and torn apart, could be orbiting Tabby's star and responsible for the intermittent dimming. In that scenario, fragments from the shattered moon, mixed with dust, might be spread around the star in a messy disk or ring. Every so often, a denser patch of that debris cloud could eclipse the star for a while, leading to the strange light curve we see. Even so, as of now, none of these natural explanations fully accounts for all the weirdness. Tabby's star remains an enigma. It's not the only star that's ever shown odd dimming behavior. Astronomers have identified a few others that also dip strangely. But Tabby's star is by far the most dramatic and well-studied case. It reminds us that even around ordinary stars, very extraordinary things can happen. We've been studying stars for centuries. And yet here is a middle-aged star, not so unlike our sun, doing something that defies easy explanation. It's a humbling reminder that there are phenomena out there beyond our current understanding. It's also a beautiful example of how science progresses, by puzzling over surprises. Tabby's star sparked a flurry of observations, from amateur backyard telescopes to professional observatories worldwide, all in an effort to gather more clues. And while an alien megastructure now seems very unlikely, the attention that idea brought helped get more eyes and telescopes on the problem, yielding data that pointed toward dust. The story isn't over yet. Tabby's star is still being watched, and each new dimming event is scrutinized. Perhaps in the coming years, a combination of more data and new theories will finally reveal what's veiling this star. Until then, the flickers of Tabby's star continue to intrigue and whisper of secrets yet uncovered. From the mystery of a single star, we now widen our view to the grandest scales, to the entire cosmos and the imprint of its earliest moments. When scientists mapped the afterglow of the Big Bang, they expected a near-uniform glow. Instead, they found a curious cold blemish in that cosmic backdrop, an anomaly that might be the result of an immense structure in our universe, or perhaps something profoundly exotic. They call this puzzling region the cosmic cold spot, a patch of sky seen in the light of the infant universe that is markedly cooler than its surroundings. The cosmic microwave background, CMB, is the faint afterglow of the Big Bang, a bath of microwave light that fills the universe in every direction, at a temperature of about 2.73 degrees above absolute zero. It's remarkably uniform, a testament to the evenly mixed primordial universe, but not completely featureless. There are tiny variations in temperature, on the order of millionths of a degree, slight ripples that eventually led to galaxies and clusters. These small, hot and cold spots in the CMB were anticipated and match predictions of our cosmological models. However, in the early 2000s, as scientists pored over all-sky maps of the CMB from the WMAP satellite, and later Planck, they noticed one spot that stood out unnervingly. This region was cooler by significantly more than the typical little fluctuations. Not by a lot in absolute terms, on the order of a few hundred microkelvins, 10^4 degrees, colder than the average, but that made it an extreme outlier in the otherwise random speckle of CMB spots. And crucially, it covered a relatively large patch of sky, much larger than a typical fluctuation. However, in the early 2000s, when this cold spot was recognized, scientists thought they might have an explanation. Perhaps, they reasoned, there was a gigantic void in the universe in that direction. A void is a region with far fewer galaxies and less matter than average. If a vast supervoid lay between us and the CMB in that direction, it could cause the CMB's photons to lose a bit of energy as they traversed it. This is due to the integrated Sachs-Wolf effect. As light falls into a gravitational well, like an area of higher density, and climbs back out, it can lose energy in an expanding universe, and conversely, crossing a large void might leave the light slightly cooler when it reaches us. A sufficiently large and underdense region could imprint an unusually cold spot on the CMB. At first, researchers looked for evidence of such a supervoid. Some surveys of galaxies reported hints of a somewhat less populated region, roughly in the cold spot's direction, but the findings were not very clear. So a concerted effort was made. Then came more detailed studies. In 2017, a team of astronomers led by Rory Mackenzie and Tom Shanks took on the challenge of mapping galaxies in and around the cold spot with great precision. They measured distances to thousands of galaxies using telescopes in Australia, getting 3D information on where matter was distributed. The result? They found no giant supervoid. Yes, there were some smaller voids, empty pockets here and there, and some clusters of galaxies too, which is normal. The universe has a cosmic web structure everywhere. But nothing like an immense 1 billion light-year emptiness that could account for the cold spot's magnitude. When they compared the number of galaxies along that line of sight to other lines of sight, it looked pretty normal. The earlier hints of a void turned out to be not nearly enough to explain the observed cold patch. This left cosmologists scratching their heads. By our standard cosmological model, often called LCDM, the chance of a random fluctuation as large and as cold as the cold spot is low, on the order of a few percent, perhaps 1 in 50. Not astronomically impossible, but certainly attention-grabbing. If it isn't a fluke of chance, and it isn't caused by an intervening void, then what? That's when more exotic ideas entered the conversation. One suggestion was profoundly bold. Perhaps the cold spot is the bruised mark of a collision between our universe and another bubble universe. In the speculative realms of inflation theory, our own universe might be just one expanding bubble among many in a larger multiverse. If two bubbles happen to collide in the distant past, it could distort the temperature of the CMB in the collision region. The cold spot, some theorized, might be the first tangible evidence that another universe once jostled ours. It sounds far-fetched, and it is highly speculative. As of now, we have no evidence of other universes beyond our own. And the cold spot, intriguing as it is not definitive proof of anything so grand. It could still be a statistical quirk, an unlikely but not impossible coincidence in the random draw of the universe's initial conditions. Or it might hint at some subtle new physics in the early universe, perhaps a relic of a phase transition, or a cosmic texture, another exotic idea involving a kind of topological defect in spacetime. For now, the cosmic cold spot remains one of the biggest question marks on our cosmic map. Scientists continue to analyze new, ever more detailed maps of the CMB from the Planck satellite and future experiments, looking for any other unusual features or for patterns that might connect to the cold spot. For now, the cold spot reminds us that even in the most all-encompassing picture, the afterglow of creation itself, there can be anomalies that challenge our understanding. It's a gentle nudge from the cosmos that there may be chapters of the cosmic story we don't fully know. And while the multiverse idea might or might not pan out, the mere possibility of it is a profound reminder of how much remains beyond the horizons of our knowledge. Amidst these subtle signals and patchy patterns in the sky, there are also particles from space that hit Earth and carry mysteries with them. Invisible to our eyes, these visitors announce themselves only when they strike our atmosphere and unleash tiny flashes of energy. These are cosmic rays, mostly protons or atomic nuclei accelerated to high speeds, and they rain down on Earth constantly. Many come from the sun or from exploding stars in our galaxy, and those are well studied. But once in a great while, a cosmic ray arrives with mind-boggling energy, the kind of energy that defies what we think the universe can produce. These are the cosmic rays from the unknown, and they hint at powerful cosmic engines, or perhaps new physics, that we have yet to understand. The tale of ultra-high energy cosmic rays begins on a calm night in Utah in 1991, an experiment called the Fly's Eye, named for its array of upward-pointing detectors resembling the compound eye of an insect, was scanning the sky above for the faint glow of particle showers. Just before midnight on October 15th, it caught something extraordinary. A cascade of particles spread over the atmosphere, the signature of a tremendous collision high above. When scientists analyzed the data, they deduced that the culprit was a single subatomic particle, likely a proton, from space that had slammed into the air. And the energy it carried was astonishing, about 3 by 1020 electron volts. To put it in perspective, that is roughly 320 quintillion electron volts, a number almost beyond comprehension. It's equivalent to a lone proton bearing the kinetic energy of a baseball pitched at 100 kilometers per hour. In the world of particle physics, that energy is absurdly high. No human-made particle accelerator on Earth can even come close to that. It's many millions of times more energetic than the protons accelerated in the Large Hadron Collider. The Utah physicists, in a mix of astonishment and humor, dubbed this particle the "oh my god" particle, because that's pretty much the reaction one has upon hearing its energy. At first, this detection was met with skepticism. Was it a fluke? Some kind of error? But in the years following, other observatories also caught a handful of similarly super-energetic cosmic rays. These later detections confirmed that the 1991 event was no mistake. It was real, and nature was indeed accelerating particles to almost unthinkable energies. These ultra-high-energy cosmic rays, often abbreviated UHECRs, are exceedingly rare. Scientists estimate that a particle with energy above 10^20 electron volts hits 1 square kilometer of Earth's surface only about once per century. To put that in perspective for a single person, even if you lived your whole life in one spot under the sky, chances are you'd never be directly hit by one of these particular particles. They're that infrequent. To catch more of them, scientists have built huge detectors. In Argentina, the Pierre Auger Observatory sprawls across 3,000 square kilometers of dry plains, with over 1,600 water-filled tanks spread out to sense the blue flashes of light made when particle showers sweep through. In Utah, the telescope array covers about 700 square kilometers with hundreds of scintillation detectors, acting like a giant net for cosmic ray events. Thanks to these efforts, we have recorded dozens of ultra-high energy cosmic rays. In 2021, one such particle was detected by the telescope array with an energy of about 2.4 by 10 by 20 eV, nearly as high as the famous "oh my god" particle. It's clear now that the universe can indeed produce particles of these extreme energies, but the pressing question is, how? The big riddle is, what could possibly hurl a proton or nucleus to such fantastic speed? Typical sources of cosmic rays that we know, like supernova shockwaves, pulsars, or even the turbulent region around a supermassive black hole, are powerful, but generally they fall short of reaching 10-20 eV. Our galaxy's magnetic fields can't even hold on to protons that energetic. Such particles, once produced, would zoom off into intergalactic space. In fact, these ultra-energetic rays must come from outside our Milky Way, and likely from within a relatively nearby part of the universe. If they travelled for hundreds of millions of years, they'd gradually lose energy by interacting with the faint microwave glow of the Big Bang, a phenomenon known as the GZK cutoff. That means whatever shoots out a 10^20 eV proton probably lies within perhaps a few tens of megaparsecs, hundreds of millions of light years, from us, cosmically close by. We suspect the culprits might be among the most violent phenomena out there. The hyperactive cores of galaxies, where supermassive black holes fire off jets of plasma at near light speed, or perhaps the sites of huge bursts, like gamma-ray bursts, or regions of intense star formation, known as starburst galaxies. These are environments where particles can, in theory, be boosted to extreme energies. Our galaxy's magnetic fields can't corral these speeding particles, so once they're launched, they travel through the cosmos, bent slightly by any magnetic fields they encounter along the way. When these epic cosmic rays strike Earth's atmosphere, detectors can work backwards, triangulating the cascade's arrival direction on the sky. However, because the particles carry electric charge, their paths are twisted and turned by cosmic magnetic fields, much like light scatters in fog. This means the direction a particle comes from when it hits Earth isn't a straight line from its source, but it gives a general vicinity. Scientists do attempt to correct for these deflections, and interesting patterns have emerged. Intriguingly, the arrival directions of many ultra-high-energy cosmic rays aren't evenly spread across the sky. There's a slight clustering towards certain patches. In fact, the distribution hints that these particles are more commonly coming from directions where the large-scale structure of the universe is denser. In other words, where there are more galaxies and galaxy clusters. This suggests that their sources might lie in those areas. For example, active galaxies in the Virgo cluster might be candidates. But a recent event delivered a twist. The 2021 particle, when astronomers traced its path as best they could, seemed to point back to a part of the sky with very little in it, essentially a cosmic void. It was as if this uber-energetic proton came from nowhere noteworthy. One astrophysicist remarked that it was pointing towards nothing at all, absolutely in the middle of nowhere. That perplexing result implies we might be missing something important. It could be that our understanding of how magnetic fields deflect these particles is incomplete, and the particle didn't actually originate exactly where it appears to point. Or it might hint that there are sources of ultra-energic particles in places we wouldn't expect. Perhaps some new kind of source, or an overlooked phenomenon in sparsely populated regions of space. The mystery of the ultra-energetic cosmic rays remains unsolved. Are they the product of known cosmic engines pushed to their extreme? Or do they require new physics beyond our current concepts? Some theorists have speculated about exotic explanations. Perhaps these particles are the decay products of a supermassive particle that formed in the early universe and survived eons until now. Or maybe they result from collisions involving cosmic strings or other topological defects in spacetime. Such ideas venture far beyond established science. But when faced with an enigma of this magnitude, scientists cast the net wide for possible answers. For the time being, research continues steadfast. Each new detected particle is like a messenger from the high-energy realm of the cosmos, carrying clues in its energy and the direction it comes from. As we gather more of them, we hope to see patterns or correlations. Maybe we'll catch a high-energy neutrino or a flash of gamma rays from the same spot, which could finally point a finger at the source. Until then, when we look up at the night sky, it's humbling to realize that occasionally, from out of that darkness, a single proton can barrel through the void and strike our world with a punch beyond anything we can create, challenging our imagination and inspiring us to continue seeking answers. As we take these mysteries to heart, we prepare to venture further. The night sky still holds countless secrets beyond the ones we've touched on here. With minds open to wonder, we journey onward, ready to discover whatever strange phenomena lie ahead in the vast expanse of space. As we drift further into our journey beyond the known, we carry with us the wonders and mysteries unveiled so far. The cosmos has shown us phenomena both beautiful and perplexing. Now, a deeper question emerges from the quiet darkness of space. Are we truly alone? For all we have seen and learned, the silence of the universe remains one of its most haunting mysteries. On a clear night, under a sky sprinkled with countless stars, it's natural to wonder if someone is looking back at us. Each star could be a sun to someone else. Each planet, a home. With billions of suns in our galaxy and billions of galaxies beyond, the odds seem to favor life beyond Earth. Yet, when we listen for voices in the dark or scan for lights in the void, we find nothing but silence. An immense and echoing quiet, often called the Great Silence. This puzzling quietude was famously captured by a question posed 75 years ago. In 1950, physicist Enrico Fermi, during a casual lunchtime conversation about aliens, asked simply, "Where is everybody?" That innocent question carries profound weight. If the universe is teeming with possibilities for life, why have we found no evidence of anyone else? This conundrum became known as the Fermi paradox. For decades, scientists have pointed radio telescopes at the sky, hoping to catch a whisper from a distant civilization. In the 1960s, projects like SETI, the search for extraterrestrial intelligence, began scanning the heavens for signals that might be more than cosmic noise. They sift through static and starlight, looking for patterns or pulses that nature alone wouldn't produce. But despite all the listening, the result has been the same: an eerie, cosmic hush. Tellingly, when humans first discovered pulsars, stars that blink in radio waves with uncanny regularity, some scientists initially wondered if they might be signals from an intelligent civilization. The first pulsar was even nicknamed LGM-1 for Little Green Men 1. It turned out to be a natural phenomenon, a rapidly spinning neutron star, not an alien beacon. Nature, it seems, can surprise us with signals that mimic life. So we tread carefully before jumping to conclusions. It's not for lack of looking. Our technology grows more sensitive each year. We've discovered thousands of exoplanets orbiting distant stars, some in zones warm enough for liquid water, and possibly life. We have even sent our own messages into the void. A radio transmission beamed toward a distant star cluster, and records on space probes carrying greetings from Earth. Decades have passed since those were sent, and we've heard no reply. The contradiction between the likelihood of extraterrestrial life and the lack of evidence is striking. The universe is old, over 13 billion years, and vast beyond imagination. Our Milky Way galaxy alone holds hundreds of billions of stars, many of them hosting planets in the habitable zone. If even a tiny fraction of those planets developed life, and a fraction of those developed intelligence and technology, the galaxy should be buzzing with signals, megastructures, or even visitors. But so far, we've found nothing. It's as if we are in a crowded forest, yet hear no birdsong and see no footprints, as if all the animals are hiding or absent. We can try to estimate how many civilizations might be out there by using a formula called the Drake equation. It's a way to break down the problem into factors. How many stars form each year? What fraction of those have planets? How many of those planets might be habitable? How often life arises on habitable worlds? How often life becomes intelligent and develops technology? And how long such civilizations last? Plugging in our best guesses, the Drake equation can yield a wide range of answers. If we're optimistic, we get a galaxy filled with civilizations, perhaps hundreds or thousands, just in the Milky Way. If we're pessimistic with the numbers, we might find that we are effectively alone. The truth is, most of these factors are still largely unknown, so the Drake equation doesn't give a single answer. Instead, it highlights how much we have yet to learn about life in the universe. Meanwhile, initiatives to listen and even send out messages continue. In 1974, astronomers used the giant Arecibo radio telescope in Puerto Rico to beam a powerful signal toward a distant star cluster, essentially a cosmic greeting card encoded in radio waves. We've also placed plaques and golden records on spacecraft, like the Pioneer and Voyager probes, carrying sounds and images of Earth out into the stars. These are small voices cast into a vast darkness, but they carry our hope that someone might find them one day. And on the listening side, projects like SETI have grown more sophisticated. Radio telescopes scan huge swathes of the sky at many frequencies, and even optical telescopes look for bright laser pulses that an advanced civilization might use to communicate. So far, nothing definitive has been heard or seen. but a single confirmed signal would change history in an instant. It's sobering to realize that our own radio and TV leakage, the unintentional broadcast of our presence, has only been traveling outward for about a century. That means an alien listening from 100 light years away or more would still hear nothing from us, because the signals haven't reached them yet. The Milky Way galaxy is 100,000 light years across, so our presence is currently a tiny expanding bubble of radio waves among the stars. Other civilizations might be similarly cocooned, only detectable within a limited range. We could be surrounded by voices, but too distant to exchange hellos. We have also started looking for other kinds of evidence of advanced civilizations. Some scientists search for techno-signatures, signs of technology, such as unusual chemicals in exoplanet atmospheres that might indicate industrial pollution or patterns of light that could come from colossal engineering projects. A famous recent example was the star nicknamed Tabby's star, which dimmed and brightened in an odd pattern. For a time, speculation ran wild that maybe a huge alien structure, like a solar energy collecting Dyson sphere, was orbiting the star and causing the dips in light. Further studies suggested a more mundane explanation, likely drifting clouds of dust. But the case opened our minds to the kinds of strange things we might look for. There are many possible reasons for this great silence. One is simply that life, especially intelligent life, might be exceedingly rare. Perhaps Earth truly is a cosmic oasis, and complex life is a fluke of improbable circumstances. Maybe the majority of planets are barren, or home only to simple microbes that never build cities or radios. If intelligence is rare enough, we could indeed be alone, or at least the first civilization in our corner of the galaxy. Another possibility is that civilizations are common, but they are not broadcasting signals in ways we can detect. Our searches mostly tune in to radio waves, a method convenient for us. But an alien society might use technologies beyond our grasp, communications based on physics we haven't discovered, or signals indistinguishable from natural background sources. It's also possible that advanced beings have no interest in communication or exploration outside their own sphere. Perhaps they turn inward to virtual realities or contemplative pursuits, losing any desire to reach out. Some thinkers have suggested that advanced civilizations might all be listening, but not transmitting, each waiting for someone else to speak first. If every society decides to stay quiet, the sky would indeed appear silent. Others imagine that broadcasting your presence could be dangerous. They spin scenarios of a dark forest cosmos, where each civilization hides, fearful that a louder, predatory civilization might hear them and do harm. In such a dark forest, everyone creeps silently among the trees, lights off, hoping no one notices them. This idea, inspired by science fiction, resonates as a possible answer. Maybe everyone is afraid to shout into the void. There is also the notion of a great filter, a stage in the journey from simple life to advanced civilization that is extremely hard to pass. Life may be common in the universe, but perhaps almost none survive long enough to colonize the stars or make contact. Possibly they destroy themselves through war or environmental collapse. Or maybe the universe itself presents hurdles, giant catastrophes like supernova explosions or gamma-ray bursts that regularly reset the cosmic stage before life gets very far. If such a filter exists, maybe we have already passed it. Or maybe it lies ahead, meaning most civilizations at our stage inevitably falter. Then again, perhaps the aliens are out there, and even abundant. But the distances are so immense that their signals have not reached us yet, or ours haven't reached them. Space is incomprehensibly large. Even our nearest star beyond the Sun is over 4 light years away. That's 4 years for light to travel at the fastest speed possible. If a civilization is 100 or 1,000 light years distant, any signal from them would take centuries to arrive, and we've only been listening for a few decades. It could be that messages are indeed out there, faint whispers traversing the dark, but they just haven't arrived at Earth yet. Time is another factor. Humanity has existed for a mere blink in cosmic terms. If other civilizations rose millions of years ago and fell, they might be long gone by the time we came around. We could have missed them by eons. Or perhaps others have not yet arisen, and we are among the first, with the galaxy's grand pageant of life still in its opening act. So the paradox remains. In theory, the cosmos should be alive with activity, yet in practice, we see none of it. This mystery of the great silence stirs both our scientific curiosity and our sense of loneliness. It makes us ask, is the silence out there, or are we just not listening well enough? Consider one striking moment in our search for company: the wow signal. On a summer night in 1977, a radio telescope in Ohio recorded a strong, unusual signal from deep space. It was unlike the usual background noise. It was narrow and focused, the kind of thing that could come from a transmitter. The astronomer who spotted it was so astonished that he scribbled "wow" next to the data printout. That one signal lasted just minutes and then disappeared, never to be heard again. For a while, excitement bubbled. Had we finally heard a call from another civilization? But without a repeat, we could not be sure. The wow signal remains an enticing mystery, possibly a fluke of nature, or perhaps a missed hello from the stars. Decades later, a study suggested that a passing comet could have emitted the unusual signal, offering a possible mundane explanation. But even that idea is not confirmed, and so the wow signal's source is still unknown, a lingering maybe in the search for company. And so we watch and listen. We send out spacecraft to explore our solar system, and we aim detectors at distant exoplanets, searching for signs of oxygen or other life markers. The James Webb Space Telescope, for example, is now able to analyze the atmospheres of some exoplanets, looking for telltale gases that might indicate living processes. So far, nothing has shouted, "I am here." Just the faint, ongoing quiet. Despite the silence, the night sky still inspires hope. Every star we see is a reminder of possibilities. As our scientific instruments improve, we might catch a whisper or glimpse a telltale sign of life in some far-off starlight. Until then, we can only theorize. Are we alone, an island of life in a vast, empty sea? Or is the universe like an ocean teeming with life, but the distances and depths keep us apart for now? This is the heart of the Fermi paradox, the gulf between what seems probable and what we observe. Perhaps one day, the paradox will be resolved. We might detect a clear signal, or find an artifact left by alien travelers. Or we might gain a deeper understanding of biology that shows us that life truly is incredibly rare. For now, it is a mystery that humbles us. It reminds us that despite all our equations and telescopes, we are but newcomers in a vast, ancient cosmos, straining our ears in an enormous dark cathedral that has yet to echo back our call. Still, silence can be deceptive. It doesn't necessarily mean emptiness. Just as a quiet forest might hide many living beings going about their lives in hushed ways, so might the galaxy abound with life that simply keeps to itself. And silence, too, can be broken at any moment. Perhaps tomorrow, a new telescope will catch a strange signal, or a probe will stumble upon something astounding. In pondering the great silence, we prepare our minds for whichever answer may come. We remain patient and curious. And as we contemplate the stillness between the stars, another thought arises. What if the silence isn't silence at all? What if we have been contacted, but in ways we do not yet recognize? Or what if evidence of others lies not in the sky, but has already visited us here on Earth, subtly and without official acknowledgement? For while our radio receivers have heard no confirmed alien message, many people claim to have seen inexplicable things with their own eyes. Strange craft in our skies, lights dancing on the horizon, objects darting and vanishing with no sound. Could it be that we have company after all, in plain sight, yet still no closer to an answer? As we leave the realm of cosmic silence, we turn to these mysterious encounters that blur the line between science and the unknown. Reports of strange sights in the sky are nothing new. Long before modern rockets or satellites, people around the world witnessed lights and objects they couldn't explain. Glowing orbs moving against the stars, disks that darted off at unimaginable speeds, silent apparitions hovering in the night. In the mid-20th century, these stories surged. Pilots from the Second World War spoke of Foo Fighters, odd, dancing lights trailing their aircraft. In 1947, a private pilot named Kenneth Arnold famously reported seeing 9 shiny objects skimming through the air, like saucers skipping on water. The press seized on his words, and thus the term flying saucers was born. One famous early case that helped launch the UFO legend was the incident at Roswell, New Mexico, in 1947. A rancher found mysterious debris in the desert, and the US Army Air Force initially announced it had recovered a flying disc. They quickly retracted that statement, claiming it was just a weather balloon. This abrupt change in story fueled suspicions. In later decades, some came to believe an alien craft had indeed crashed and was covered up by authorities. The Roswell incident, whether mundane or extraordinary, became a cultural touchstone, symbolizing the possibility that visitors from beyond might have already come, quietly and without official acknowledgement. Since those early days, the phenomenon of UFOs, unidentified flying objects, has captivated the public imagination. For decades, sightings poured in. Strange metallic craft seen by airline crews, bright triangular formations of lights over quiet suburbs, spinning discs recorded on shaky home videos. Most sightings had mundane explanations: stars misidentified, weather balloons, experimental aircraft, or optical illusions. But a hard core remained puzzling, defying easy dismissal. Governments took notice, albeit quietly at first. The United States Air Force launched investigations like Project Blue Book in the 1950s to study UFO reports. They catalogued thousands of cases, from everyday misidentifications to truly puzzling encounters. By the end of the 1960s, the official stance was that nothing conclusive had been found, no evidence of extraterrestrial craft, and the project was closed. Publicly, interest waned, and UFOs became the stuff of science fiction and folklore. Throughout the Cold War, however, UFO sightings often stirred anxiety behind the scenes. Military officials wondered if those unidentified objects could be secret aircraft or weapons developed by rival nations. In many cases, they were indeed advanced human technology being tested in secret: high-altitude spy balloons or prototype planes flying higher or faster than anyone knew possible. But not all sightings were so easily explained. For instance, between 1989 and 1990, Belgium experienced a wave of UFO reports. Hundreds of people, including police officers and pilots, witnessed large triangular craft with bright lights cruising silently over the countryside. The Belgian Air Force even scrambled F-16 fighter jets to intercept these objects. Mysteriously, the jet's onboard radar picked up targets that accelerated and maneuvered in ways far beyond conventional aircraft. The triangles eventually disappeared, leaving Belgium and the world with more questions than answers. In 1980, on the other side of the world, US Air Force personnel at a base in England reported a bright, metallic object darting through the woods of Rendlesham Forest, an episode that remains shrouded in mystery. And in 1997, thousands of witnesses across Arizona watched a huge V-shaped array of lights glide silently overhead in what became known as the Phoenix Lights incident. These famous encounters, like many others, yielded no definitive evidence of aliens, but they illustrate how persistently and globally the UFO phenomenon manifests, challenging us to explain the seemingly unexplainable. Other countries have had official inquiries too. France's National Space Agency, for example, has long maintained a department to collect UFO reports, treating them as phenomena worthy of serious study. They, like others, find that the vast majority of cases turn out to be misidentifications or natural phenomena, but a small percentage defy any obvious explanation. Even the former Soviet Union logged encounters by cosmonauts and radar operators that they couldn't easily resolve. It seems wherever humans watch the skies, a few perplexing sights are bound to appear. Yet in recent years, the topic has re-emerged with surprising credibility. Military pilots and sailors have come forward with cockpit videos and sensor data showing objects moving in astonishing ways. These aren't anonymous cranks, but trained observers, often with multiple instruments backing up their accounts. Footage has been released of an object shaped like a white tic-tac candy darting away from US Navy fighter jets off the coast of California, outrunning and outmaneuvering them with ease. In another incident, infrared cameras captured a pill-shaped craft hovering and rotating against high winds with no visible means of propulsion before it zipped away. The pilots who witnessed these events were left both baffled and wonderstruck. They knew of no aircraft on Earth that could perform like that. The terminology even changed. UFOs are now often called UAPs, unidentified aerial phenomena, reflecting a new willingness to study them seriously without stigma. Government agencies have set up task forces to collect and analyze reports. An official report in recent times catalogued hundreds of such encounters, of which a significant number could not be confidently explained as balloons, drones, or natural occurrences. The report made clear it had no evidence of alien origin, but the sheer number of unexplained cases was itself remarkable. This led to something once unthinkable. In 2022, the US Congress held public hearings about UFOs for the first time in over 50 years. High-ranking officials testified that while many cases had prosaic explanations, some incidents remained genuinely unexplained. The Pentagon established a new office dedicated to investigating UAP incidents across the military, aiming to standardize reporting and delve into these mysteries systematically. Even NASA convened a panel of experts to study UAP reports, stressing that examining the unknown is part of science. Public attitudes toward UFOs have indeed shifted. What once was ridiculed as fringe has gained a degree of respectability, largely because of credible testimony and official acknowledgement that something is truly not understood. In the past, someone claiming to see a flying saucer might have been met with smirks. Today, a fighter pilot or astronaut can calmly describe a strange encounter and be taken seriously enough that investigators will follow up. The stigma is lifting. Curiosity is taking its place. Amid the serious investigation, it's also true that the UFO world has its share of misinformation and lore. Hoaxes have abounded over the years, from fake photographs of saucers to imaginative tales of alien abductions. These capture public attention, but often collapse under scrutiny. Separating truth from fiction is a constant challenge. Scientists and investigators emphasize that extraordinary claims require extraordinary evidence. So far, we have tantalizing videos and puzzling radar traces, but not the kind of hard proof that would remove all doubt. No recovered alien craft or materials that defy earthly origin. No clear photograph of a spacecraft at close range. No indisputable message from ET. The lack of definitive evidence doesn't mean the phenomena aren't real. It just means we haven't pinned them down yet. And that keeps the door to speculation open, just a crack, fueling continuing intrigue. If nothing else, the study of UFOs and UAP reminds us to keep an open mind without letting our brains fall out. It's a delicate balance between curiosity and skepticism. Maybe all the unexplained sightings will turn out to have earthly explanations. New types of plasma weather, rare optical illusions, secret advanced aircraft, or things we simply misinterpreted. That outcome would still be fascinating, revealing new aspects of our world or our technology. On the other hand, if even one sighting out of the thousands truly is a vehicle from an extraterrestrial civilization, a probe from afar, or evidence of physics we don't yet understand, then we stand on the brink of one of the most profound discoveries in history. Either way, investigating the unknown in our skies is a worthwhile endeavor. It pushes us to improve our observation tools, to sharpen our analytical methods, and to acknowledge the limits of our current understanding. Bafflingly, even in an age when nearly everyone carries a camera, clear evidence of UFOs remains scant. Sightings are often fleeting, appearing as sudden lights or distant shapes that cameras struggle to capture in focus. Skeptics point out that if alien craft were truly visiting, by now we should have crisp photographs or definitive videos. Believers counter that the phenomenon might not perform on cue for our devices, or that perhaps these objects have ways of obscuring themselves. So the photographic proof remains as elusive as the objects themselves, adding yet another enigma. For many people, UFOs stir something deep in the imagination. They tap into our longing for connection and our hope that we might not be alone in the cosmic ocean. The very idea that there could be other intelligences, perhaps benign, perhaps far advanced, visiting us, or at least watching, is both thrilling and daunting. This cultural fascination has woven UFOs into our folklore and media. They appear in movies, inspire novels, and spark late-night conversations under starry skies. We gaze up and see a light moving oddly and feel both a thrill and a mystery. That emotional response, a blend of wonder, curiosity, and a touch of fear, keeps the topic of UFOs alive in the public mind as both a scientific question and a personal intrigue. Each story, whether ultimately explainable or not, reminds us that there is much we don't understand. The UFO phenomenon sits at the edge of the known and the unknown, where perception meets mystery. It forces us to admit that not all things can be neatly categorized, at least not yet. Could some of these sightings be glimpses of a truth we are not yet ready to grasp? Or will they turn out to be misunderstandings of natural or human-made phenomena once we investigate fully? For now, UFOs and UAPs remain a genuine enigma. They spark our imagination because they hint that the answer to Fermi's haunting question, "Where is everybody?" might be closer than we think, but just out of reach. If even one sighting out of the many is indeed evidence of an extraterrestrial presence, it would transform our understanding of our place in the cosmos. But until that day of confirmation, we balance between open-minded wonder and careful analysis. Either way, the UFO question has brought a piece of the mystery down to Earth's skies. It suggests that the unknown isn't only light years away. It might be right above us, visiting fleetingly and vanishing. This notion is both thrilling and unsettling. It reminds us to keep looking up, not just to scan the distant stars for signals, but to watch our own skies for the unexpected. As we muse on lights in the sky and what they could mean, another story of the unknown unfolds. Not in our atmosphere, but from far beyond it. Just a few years ago, we discovered something that travelled untold distances to reach our solar system. It came without warning, stayed briefly, and then departed, leaving more questions than answers. It wasn't a sighting on Earth, but an object passing through our cosmic neighbourhood, a visitor from the stars that we call Oumuamua. When astronomers realised Oumuamua came from beyond our solar system, it marked a milestone. In late 2017, astronomers in Hawaii spotted a faint point of light moving rapidly across the sky. At first, it seemed like an ordinary small asteroid or comet passing by. But calculations quickly revealed something astonishing. This object was not bound to our sun. It was travelling so fast and on such a trajectory that it must have come from interstellar space, from another star system entirely. We had never seen anything like it before. Astronomers gave it the name Oumuamua, a Hawaiian word meaning scout or messenger from afar, a fitting tribute to its status as the first known visitor observed from beyond our solar system. Oumuamua was tiny and distant, never bright enough to see with the naked eye. Astronomers rushed to train their telescopes on it during the few weeks it was visible. The more they observed, the stranger it appeared. Unlike a comet, it showed no hazy tail of gas or dust as it neared the sun. It was tumbling end over end, and its brightness changed dramatically during each rotation, suggesting an odd, elongated shape. Some estimates implied it might be extremely long and thin, perhaps cigar-shaped, or maybe very flat, like a pancake, spinning as it went. No asteroid or comet we'd seen had such an extreme shape. It was something genuinely new. Scientists tried to trace Oumuamua's origin. Based on its path, they projected backward to see if it came from any known star or region, but there was no clear match. It seemed to have been travelling through the galaxy for millions of years, wandering the interstellar void, before fate brought it near our sun. Perhaps it was ejected from its home star's planetary system long ago by a gravitational encounter, a rogue fragment from some distant world. In that sense, Oumuamua could be like a message in a bottle from a far-off shore, a piece of another world's history cast into the sea of space, arriving unexpectedly on our doorstep. One of the first things researchers checked was whether Oumuamua was transmitting any radio signals, just in case it wasn't natural at all. Radio telescopes listened for any hint of an artificial beacon as the object passed by Earth. The result was silence. No detectable radio emissions. If Oumuamua was a probe or craft, it wasn't sending out anything obvious. That finding, combined with its lack of a comet tail, pointed toward it being a natural object. But natural did not mean ordinary. As Oumuamua sped away from the sun, it did something unexpected. It didn't follow exactly the path that gravity alone would dictate. It had a slight excess acceleration, as if something gently pushed it outward. With comets, such non-gravitational motion usually comes from jets of gas erupting as ice vaporizes in sunlight, a bit of rocket-like thrust. But telescopes saw no signs of such jets on Oumuamua. No cloud of dust, no visible outgassing at all. The object was perplexingly behaving like a comet without looking like one. This opened the floodgates to speculation. Scientists proposed various ideas. Perhaps Oumuamua was made of a different kind of ice that produces gas we cannot easily detect, like frozen hydrogen that would vent off invisibly or be so quick to dissipate that we'd miss it. Or maybe it was a shard of solid hydrogen or nitrogen ice, chipped off from an ice-rich exoplanet, or the frozen crust of a distant dwarf planet, slowly evaporating as it warmed near our sun. Others suggested it could be a fragment of a larger body, torn apart by a star's gravity and flung out into the galaxy, destined to wander forever. Then there were more exotic hypotheses. A prominent astronomer raised the possibility that Oumuamua might not be natural at all, but an artifact, perhaps a defunct probe or a light sail sent by an alien civilization. This idea was controversial, met with intrigue by some and skepticism by many. Most scientists lean toward a natural explanation, yet they all admit Oumuamua is unlike any space rock we've encountered before. Extraordinary claims require extraordinary evidence, and so far, Oumuamua has offered tantalizing hints, but no definitive answers to prove it artificial. It made us wonder, was it a scout of some kind, as its name implies? A messenger bearing news from the greater galaxy? Or simply a natural fragment of a distant realm, unknowingly carrying the story of its origin encoded in its composition? Unfortunately, our chance to learn more was fleeting. By the time its unusual behavior was understood, Oumuamua was already exiting our solar system, fading from view. No spacecraft was anywhere near it, and we could only watch as it slipped away into the darkness, bound for the stars once more. It left behind a tantalizing mystery. A piece of another star system had come to visit and challenge our assumptions, then disappeared before we could unravel its secrets. By then, debates about its nature, natural oddity, or something more had to continue without new data. Most experts suspect it was a peculiar natural object, but nobody can be certain. With no additional observations possible, the mystery remains unresolved. Oumuamua did give us a parting gift, the realization that interstellar objects do wander through our solar system from time to time. In fact, 2 years later, in 2019, another visitor from afar was spotted, a comet named 2I Borisov, clearly carrying the telltale coma of dust and gas. Unlike Oumuamua, Comet Borisov looked and behaved much like comets we know, suggesting that many interstellar travelers might be fairly ordinary after all. That only made Oumuamua more special. It was an outlier, a surprise that forces us to ask what else might be out there that we've never seen. The cultural impact of Oumuamua was also notable. Science fiction fans couldn't help but recall Arthur C. Clarke's novel Rendezvous with Rama, where a mysterious cylindrical alien starship enters the solar system. The parallels were hard to ignore. Here was reality presenting something uncannily similar, an enigmatic object from the stars. If Oumuamua had been a probe or vessel, it gave no sign of trying to communicate or alter its course deliberately. No flashing lights, no slowing down as it neared Earth, just a silent flyby. If it was an alien craft, it might have been derelict or simply uninterested in us. Still, the scenario sparked public imagination. It felt like a chapter of science fiction come to life. Realistically, most of the scientific community favors a natural explanation for Oumuamua, an exotic piece of nature to be sure, but not a spaceship. Yet the door isn't entirely closed. The data we gathered were limited by distance and time, leaving room for educated guesswork. and speculation can be healthy in science, as long as it inspires further investigation. Oumuamua's visit has already spurred new ideas and initiatives. Some scientists are devising plans for interstellar object interceptors, spacecraft that could be launched on short notice to chase down future interstellar visitors for close examination. They're also expanding sky surveys to catch similar objects earlier in their approach. Indeed, now that we know such visitors exist, we're on the lookout for the next one. Comet Borisov's discovery showed that Oumuamua was not a one-off event. The galaxy sends us samples of other star systems. The difference is, Borisov turned out to be familiar, while Oumuamua remains an intriguing oddball. We know that our own solar system likely flings out debris into interstellar space, comets and asteroids that get gravitationally tossed into the void. Likewise, other stars should eject material as well. Oumuamua was the first we observed passing through our neighborhood. It's quite possible many more have slipped by unnoticed over the millennia. Now that we are paying attention, the next one might not catch us by surprise. Watching Oumuamua depart, one couldn't help but feel a mix of wonder and melancholy. In the blink of an eye, in astronomical terms, it was gone, back into the quiet between the stars. We are left with our questions and our imagination. And as we ponder that interstellar mystery, we also turn our gaze back to places much closer to home. Sometimes the strangest phenomena are not only far away or high above, but on the very worlds next door. Mars, often called the Red Planet, has long been a focal point in the search for extraterrestrial life. Cold, dry, and seemingly barren today, Mars was not always so forbidding. Decades of exploration have revealed that Mars once had rivers, lakes, and possibly even a vast ocean. Where water flowed, life might have had a chance. We haven't found little green men or ancient Martian cities, but scientists have discovered tantalizing clues that Mars might not be entirely dead even now, or at least that it preserves the fingerprints of past life, if it ever existed. Decades ago, when the first spacecraft visited Mars, scientists were already hunting for signs of life. In 1976, NASA's Viking landers conducted experiments on the Martian soil that gave puzzling results. One test, designed to detect microbial metabolism, came out positive. The soil released gases as if something in it was consuming nutrients. But other tests, including one that searched for organic molecules, found none. The mixed signals left scientists divided. Did Viking glimpse a trace of Martian microbes? Or were those results just odd chemistry in reactive soil? To this day, some researchers argue that Viking's life detection experiment might have found something alive, while most believe it was a false alarm caused by unfamiliar soil chemistry. The verdict remains elusive, and it showed us how careful we must be in interpreting alien data. Our view of Mars has evolved tremendously over time. In the late 19th century, some astronomers mistakenly thought they saw a network of straight canals on Mars, an optical illusion that led to fanciful theories of a dying Martian civilization irrigating its deserts. Those ideas turned out to be false, but they sparked public fascination with Mars as a potentially inhabited world. By the mid-20th century, spacecraft flybys and orbiters revealed a cratered, barren surface, and Mars seemed lifeless after all. Yet, paradoxically, the more we studied Mars, the more evidence we found that it was once much more Earth-like. Dry riverbeds, ancient lake basins, and minerals that form in water all pointed to a planet that long ago had rain, flowing water, perhaps even a northern ocean. So the question shifted. If not little green men, could Mars have hosted simple life like microbes in those wet eras? And might some tiny life persist even now in hidden refuges? One of the most intriguing findings on Mars today is a simple gas: methane. On Earth, methane is often a byproduct of life, released by microbes in wetlands or by the digestion of larger animals, though it can also come from geological activity, like reactions between water and certain rocks. Mars has a very thin atmosphere, and any methane present should be broken down by sunlight in just a few centuries. So if you detect methane on Mars now, something must have released it recently. In 2003, scientists using telescopes on Earth reported a whiff of methane in the Martian atmosphere, sparking both excitement and skepticism. The measurements were difficult and at the edge of detection. Some questioned if the methane was real. Then, in 2012, NASA's Curiosity rover landed on Mars, equipped with a sensitive chemistry lab. Curiosity sniffed the Martian air and initially found almost no methane. But later, it detected sudden spikes of methane on a few occasions. The levels would rise for a time, then dissipate, almost as if Mars itself breathed in small gasps. More intriguingly, a seasonal pattern emerged. Methane readings seemed to climb in the Martian summer and drop in the winter. This methane mystery on Mars has scientists scratching their heads. Could it be microorganisms hidden deep beneath the surface, periodically releasing gas into the air? If not life, then what? Perhaps chemical reactions under the ground. For instance, water interacting with minerals in a process known as serpentinization could produce methane and occasionally vent it out. Yet attempts to find a clear source have come up empty. The European Trace Gas Orbiter, circling Mars since 2016, has so far failed to detect the methane that Curiosity found from the ground, adding another layer of confusion. It's possible that the methane is localized, appearing in pockets or bursts that the orbiter, which scans the whole planet from above, averages out and misses. Or perhaps the rover's detections were due to some transient, unexplained process we haven't yet unraveled. Methane isn't the only hint Mars has given us. Mars rocks have yielded organic molecules, carbon-containing compounds that are the building blocks of life, preserved from billions of years ago when Mars was wetter. In 2018, the Curiosity rover drilled into ancient mudstone and detected complex organics locked in the rock. These organics don't prove life existed. Such molecules can be made by non-biological chemistry as well. But their presence shows that the raw ingredients for life were present on Mars in the past. Additionally, back in 1996, scientists made headlines with a Martian meteorite found on Earth, known as ALH 84001, that seemed to contain microscopic structures resembling fossil bacteria. The scientific debate over that claim continues to this day, with many experts leaning toward non-biological explanations for those tiny shapes and chemical signatures. Still, the possibility lingered in the public mind. Could there have been life on Mars that left even a tiny trace in a rock? In recent years, beyond methane, other intriguing findings have emerged on Mars. For example, dark streaks have been observed on certain Martian slopes that appear and fade with the seasons. At first, scientists thought these streaks might be due to trickles of liquid water, salty brines that briefly wet the surface during warm times. This raised excitement that some micro-habitat of liquid water, however transient, could exist on Mars today. However, further analysis suggested these so-called recurring slope lineae might actually be dry flows of sand and dust with no water necessary. The jury is still out. If any liquid is involved, it might be very temporary or limited. But even the chance of occasional brines keeps the question of present-day life open a crack, because where water flows, life as we know it could potentially find a foothold. There's also evidence that Mars still holds water deep below the surface. In 2018, radar reflections from a European Mars orbiter suggested the presence of a stable pond of liquid water beneath the ice of Mars's south polar cap. If true, this subglacial lake, perhaps made liquid by salts and pressure, would be an environment that could conceivably support life today, protected from harsh conditions above. Some scientists are cautious, proposing alternative explanations for the radar signal, like a layer of unusually water-rich sediment or brine-soaked clay rather than a true liquid lake. But if it is liquid water, that's a big deal. It would mean Mars has a persistent, wet environment, a potential haven for life, on a planet that seems utterly desiccated on the surface. To find out the truth, we keep exploring. NASA's Perseverance rover is currently roving an ancient Martian lakebed, drilling out cores of rock that might contain evidence of past life, perhaps fossilized microbes from a time when Mars had water aplenty. Perseverance is storing those samples in sealed tubes that a future mission will pick up and bring back to Earth, so we can analyze Martian rocks in our best labs for signs of ancient life. Meanwhile, scientists scrutinize every new bit of data from Mars orbiters and rovers, looking for anomalies. Even today, Mars manages to surprise us, be it a spike of gas, an odd chemical in the soil, or a strangely textured rock that makes us wonder if it might be a fossil of some microbial colony. Mars remains an enigma, a world that was once more familiar, with rivers, lakes, possibly blue skies and white clouds, that became hostile and quiet. If life took hold there long ago, did it perish when the planet changed? Or does it endure, hanging on in some refuge like underground caverns or pockets of salty water? So far, we have no clear evidence of living organisms on Mars. We have only clues that tease us from the boundary of certainty. It could turn out that all the methane and organics are purely chemical, nothing to do with biology. But until we know for sure, Mars keeps us guessing, forcing us to rethink what we know about life's tenacity and where life might thrive. Now consider Venus, Earth's twin in size and gravity, but in reality, a hellish contrast to our world. Venus's surface is unimaginably harsh, hot enough to melt lead, crushed by an atmosphere 90 times thicker than ours, and soaked in clouds of corrosive sulfuric acid. For a long time, the idea of life on Venus seemed almost impossible given those extreme conditions. Yet Venus, too, has presented a puzzle that made scientists reconsider the impossible. In 2020, a team of astronomers announced they had found the spectral signature of the gas phosphine in Venus's upper atmosphere. This caused a stir, because on Earth, phosphine is a gas associated with living things. It's found in places where microbes thrive, such as swamps or the guts of animals, and it's also produced artificially by humans in industry. The reason this finding was so provocative is that phosphine shouldn't be common on a rocky planet without life. It's a molecule that is destroyed quickly by sunlight and reactive chemicals, and there are very limited ways to make it without biological processes, especially in an oxygen-poor environment like Venus's. The researchers used powerful telescopes to observe Venus's clouds and detected what looked like the chemical fingerprint of phosphine gas. The concentration was tiny, just a few parts per billion, but if real, it begged for an explanation. Immediately, scientists around the world began scrutinizing this result. Could something non-living on Venus be making phosphine? Some proposed exotic chemistry, maybe volcanoes belching out a mix of gases that, under Venus's extreme conditions, form phosphine. Or perhaps lightning in the atmosphere triggers unusual reactions. Others pointed out that the data might have been misinterpreted. Maybe the signal attributed to phosphine was actually from a more ordinary substance, or just a mistake in analysis. Follow-up studies have been mixed. A few later observations also hinted at phosphine, though sometimes at lower levels. Other attempts found nothing conclusive. The debate is ongoing, but the mere possibility of a biomarker gas in the Venusian clouds reignited interest in our cloud-shrouded sister planet. If not life, what then could account for it? And if it is life, what kind of life could survive in Venus's clouds? Back in the early 1960s, an astronomer named Carl Sagan speculated about that very scenario. He suggested that while Venus's surface was inhospitable, the upper atmosphere, about 50 kilometers up, where the pressure and temperature are much more Earth-like, could host airborne microbes. They might float in droplets of sulfuric acid and water, reproducing and metabolizing in the mild temperatures of those high altitudes. For decades, this idea was largely forgotten or regarded as fanciful, especially after spacecraft confirmed how extreme Venus's surface conditions are. Yet now, with phosphine on the table, Sagan's old speculation suddenly doesn't seem so far-fetched. Scientists are seriously considering that if life ever arose on Venus, perhaps back when Venus was cooler and had oceans, billions of years ago, it might have adapted by retreating to the only habitable niche left, the temperate cloud layers high above the scorched surface. Besides phosphine, Venus presents other enigmas. Observations in ultraviolet light show dark patches in Venus's cloud tops, areas that absorb more UV radiation than the rest of the clouds. The substance causing these dark patches is unknown. Scientists simply call it the unknown UV absorber. One whimsical hypothesis is that vast colonies of microbes could be living in the clouds, and that their biological pigments are absorbing the UV light. It's highly speculative, but it's an example of how Venus keeps throwing curveballs at us. There may be strange chemistry happening in those clouds that we have yet to understand, possibly involving sulfur or other compounds, or maybe something we haven't even thought of. The Venus puzzle, much like Mars's methane, highlights how little we truly know about our nearest planets. Both cases teach a humbling lesson. Life might announce itself in indirect ways, or conversely, we might fool ourselves into thinking we've found life when it's really just unfamiliar chemistry. The only way to know for sure is to investigate further. And that is exactly what upcoming missions aim to do. To solve these mysteries on Venus, forthcoming missions are being prepared. NASA is planning a mission called Da Vinci, which will send a probe to plunge through Venus's atmosphere in the coming years. As it descends, it will directly sample the clouds and measure their gases, potentially confirming whether phosphine is truly there and in what quantity. Another mission, NASA's Veritas orbiter, will map Venus's surface with high-resolution radar and study its geology, which may indirectly shed light on atmospheric chemistry, for instance, by seeing if Venus has active volcanoes that could contribute gases. The European Space Agency is sending a probe called Envision to further investigate Venus's atmosphere and surface. There's even discussion of designing aerial platforms, essentially balloons, that could float in Venus's upper atmosphere for extended periods, acting as robotic laboratories to sniff out chemical and possibly biological signatures. All of these efforts, motivated in part by the phosphine findings, will bring us closer to answering the question of whether Venus's clouds could host life, or if there's a non-biological chemistry we've overlooked. Mars, too, continues to be a focal point of exploration. In addition to NASA's rovers, other countries and private ventures have ambitious plans for the red planet. The hope is that within the next decade or two, we will retrieve the rock samples that Perseverance is collecting and bring them to Earth, a complex, multi-mission effort, so we can examine Martian soil in unparalleled detail for any signs of ancient life. There's also talk of human missions to Mars in the not-too-distant future. human explorers, with their ability to make quick decisions and use advanced tools on site, could dramatically accelerate the search for life's evidence on Mars, drilling deeper and covering more ground than robots can. Even if Mars proves sterile today, finding proof that it once hosted microbes, say fossils in an old dried-up lake bed, would be a discovery of immense significance, teaching us that life can start on two neighboring planets and raising the odds that life is common in the universe. Whether these hints, the Martian methane and Venusian phosphine, turn out to be signs of life or signs of intriguing chemistry, the impact is profound. If they indicate life, then life is not unique to Earth. It means biology springs up on at least two planets in one solar system, and possibly on countless worlds across the cosmos. If they are ultimately just chemistry, then nature has more tricks up her sleeve than we knew, and we will have learned something new and fundamental about planetary processes. Either result is a win for knowledge. As of now, both Mars and Venus keep their secrets close. Mars has not revealed any living organisms to our cameras or instruments, and Venus's clouds remain enigmatic and unsampled. But the sense of potential, that tantalizing maybe, has grown stronger. We can envision a future where a microscope on Mars finally images a tiny living cell in the soil, or a balloon in Venus's skies detects organic molecules that only life could produce. These scenarios are still speculative, but not impossible. What Mars and Venus teach us is to expect the unexpected. In seeking life in the cosmos, we began by looking far away, listening for radio signals from distant stars. Yet here, right in our cosmic backyard, were subtle hints that maybe life, or something resembling it, might be playing out under our noses. It's a reminder that the unknown isn't always light years away. Sometimes it's on the next planet over. And in light of these Martian and Venusian riddles, scientists are indeed broadening their definition of what is habitable. A planet once thought dead can surprise us with a hint of life's chemistry, and a world deemed too hostile might harbour a life-friendly niche. Mars shows that even a long-gone ocean can leave behind ghostly signs that something may have lived. Venus suggests that life might adapt to hide in the one temperate layer of a furnace world. These possibilities encourage us to cast a wider net in our search for life, keeping our minds open to living worlds that may not resemble Earth at all. From the silent Martian deserts to the acidic skies of Venus, our neighbouring worlds urge us to keep an open mind. They prod us with mysteries that could redefine life itself, or simply deepen our understanding of how unique Earth may be. Either way, we are compelled to continue asking questions, sending explorers, and learning as we go. Having journeyed through these mysteries, the great silence of the cosmos, the uncanny aerial encounters, the interstellar visitor, and the enigmatic hints on nearby worlds, we find ourselves at a crossroads of knowledge and wonder. Each puzzle we explored has reminded us how much remains unknown. Yet rather than being discouraged by these mysteries, we can choose to embrace them. In the end, the unknown is not just something to solve, it is something to cherish, for it drives us to explore, to imagine, and to push the boundaries of science. Now, as we come to the conclusion of our journey, we reflect on what all these unsolved phenomena mean for us. Beyond the facts and theories, there is a deeper message in living with the unknown. It's time to step back and take in the bigger picture of our quest, to find a sense of peace with the mysteries that remain. Our exploration beyond science comes to a gentle close here, not with absolute answers, but with a reverence for the questions that endure. The universe is vast and deep, and our understanding is like a small boat on an endless sea. But it's a boat that carries hope, curiosity, and the indomitable human spirit of discovery. In this odyssey, beyond the frontiers of knowledge, we ventured from the depths of interstellar space to mysteries in our own celestial backyard. We pondered the eerie stillness of the stars and asked why other voices haven't joined the cosmic chorus. We followed tales of uncanny lights dancing in our skies, blurring the line between fact and folklore. We chased an interstellar wanderer that slipped through our solar system like a visitor in the night. We searched for whispers of life on the planets next door, wondering if we are surrounded by cosmic neighbors or simply encountering strange chemistry. Each chapter of our journey brought us face to face with the unknown and stirred our sense of wonder. One striking thing about these enigmas is how they unite us. Under the blanket of the night sky, differences of nation or culture fade. We are all simply humans, together on this pale blue dot, looking up and wondering. The pursuit of answers becomes a shared endeavor. Astronomers, engineers, poets, and everyday stargazers all play a part. We swap stories, compare notes, and pass knowledge from generation to generation. The questions we face are so vast that only through our collective curiosity and effort can we hope to answer them. In a way, the unknown is a gift that brings humanity together, giving us a common cause in our desire to understand. It's often said that the journey is as important as the destination. In science and exploration, this rings especially true. While we crave answers, the process of searching teaches and inspires us, sometimes in ways more profound than the answers themselves. The mysteries keep us humble, but also drive our progress. In trying to hear alien signals, we invent ever more sensitive instruments, and often discover new natural phenomena along the way. In chasing UFO reports, we sharpen our observation skills and remind ourselves how much we have yet to learn about even our own atmosphere. In probing Mars and Venus, we develop technologies that could one day take us there, and we deepen our understanding of how planets work. Thus, even before we find what we seek, the quest itself helps us grow. Perhaps one day, not too far in the future, some of these puzzles will be solved. We might tune in to a clear, unmistakable signal from a distant civilization. We might finally scoop up Martian soil and see a microbe wriggling under a microscope. Maybe we'll identify the physics behind those peculiar aerial phenomena, or pinpoint exactly what Oumuamua was. Those moments would be extraordinary, new chapters in the story of humanity and the cosmos. And when they come, we will celebrate. Yet, if history is any guide, each answer will lead to new questions. The horizon of the unknown will keep moving forward, always just out of reach, inviting the next generation to push further into the great beyond. Realizing that there will always be new mysteries is, in a way, comforting. It means humanity's story of discovery will never truly end. We are part of a universe that is constantly revealing itself, layer by layer. There will always be something more to learn, to explore, to marvel at. This endless frontier is one of the most beautiful aspects of existence. It ensures that our descendants and their descendants will have their own adventures in uncovering truth, just as we have ours. So, as we conclude this exploration, we do so not with a sense of finality, but with gratitude and optimism. We are grateful to live in a universe that challenges us with deep questions, and grateful for the human capacity to attempt answers. We have found comfort in not knowing everything, in being part of a cosmos that still holds secrets. The unknown, once perhaps a source of fear or anxiety, becomes a wellspring of inspiration, a treasured companion that propels us forward into tomorrow. As Carl Sagan aptly said, somewhere, something incredible is waiting to be known. That sense of anticipation is what propels us onward, reminding us that our next great discovery might be just over the cosmic horizon. Thank you for accompanying us on this voyage of discovery. May the mysteries of space inspire you to look up in awe, and may the vast silence beyond Earth fill you not with loneliness, but with a serene sense of connection to something greater. The journey beyond science never truly ends. It is, in fact, just the beginning of endless possibilities. Safe travels, fellow explorers, and good night.